the answer. Okay. Yeah. Some of the details we already discussed, but this is some more experimental setup, you can say. Yeah. So the data set we used, it has 5,000 labeled samples. So it has some 5,000 prompts basically, and some are malicious and some are non-malicious. Okay. And you can find this one online, it's available. Yeah. So it's called safeguard prompt injection. Okay. And for the execution environment, Google Colab was used. I don't know if anyone of you use Google Colab. Any programming you want to do, it has nice set of libraries. Yeah. So you can use it. And these are some hyperparameter details. Yeah. Number of epochs, like how much training you want to do. So there should be a stopping point. Yeah. Otherwise it can go forever. And these are the some libraries used. Yeah. You might have heard, if you want to do anything with AI, PyTorch, or there are lots of other, yeah, from different companies, you can use this. Now this is the accuracy result. So there are different models, and this is the one we proposed, yeah, the one you saw, the workflow. And these are some existing approaches, yeah, logistic regression, XGBoost, random forest. So these are also very popular, yeah, those three. So if we look the accuracy of everything, so we are getting a bit better accuracy in comparison to those. And you know, when we are dealing with some models, we always want accuracy close to 100%, but it's never. That means if it's close to 95 or more than 95, it's better. Yeah. So you can see we are getting very high accuracy. But like I said, if you get in something, typically you pay in something else. Yeah. But if you look the training time for our approach, it's a lot. Yeah. So logistic regression, it's just regression modeling. Yeah, it can be in fraction of seconds. XGBoost and random forest, they are in like 4 or 5 seconds, but our approach takes 40 seconds to train. Yeah. Again, for inference, you can see those approaches are taking much less time. These are the milliseconds, and ours take around 1.4 milliseconds. So you can say we are kind of trading off training time or inference time with the accuracy that we are getting. Okay. So there is always a trade-off. Okay. Yeah. Okay. So again, I think this one you may find relaxing and interesting. So this was one of the attacks on AI models, right? Prompt injection attack. So with this, I wanted to check, can you think of other attacks that can happen on AI models? So let me try that slide, that web page. Yeah. Look at this one. It does not work from there, so we have to try from here. Let's check, maybe it works. No. So typically I don't need to change anything, just in the slide it works. So not, so go here. Okay, if we look the web, I think it should be there. The thing is, if you are working on AI and little bit on security of them, you may have heard something. Okay, data poisoning, yeah, that's one very interesting attack, and there is a lot of research on it. So, you know, all the AI models are trained with some data, right? And then data poisoning is like you make some extra data from yourself, but that data has some kind of malicious contents. So you train the same model again with this data. So after it is trained, if someone tries to get an answer, it's not going to give, basically if it's kind of a classification, it may give you wrong answers. Yeah. So for example, some of the attacks that had been done, it's about like kind of a speed limit on the traffic roads, right? Sometimes it's like 60, 70, 80, or sometimes this is stop sign. Yeah. So let's say if your car is driving and someone, if AI model is doing that recognition, yeah, if it is trained with some malicious data by adding some noises in the data, then it may say this is not a stop. Yeah, in place of 60 it may say it doesn't recognize, or it might be some different speed, maybe 6 it can read 80. Yeah, so these kind of things can happen. Yeah, so jailbreaking is another thing, like basically you kind of go and change something in the model. Yeah, and it can be anything, again, something with the data, something with the model. Yeah, upload malicious file in AI model, it is more or less the same. Yeah, so you train it with some malicious contents. Yeah, file could be image or some text, whatever. Yeah, okay. Imagine all the chat bots, yeah, that we have, this chat GPT or Gemini or from Meta, yeah, all of them. If you get access, you can train it with some data, right? And then it may give some kind of response that those companies don't want. Yeah, so that is why these models are very, very closed. Yeah, there are some open source one, so you can take that, you can make them malicious, but not all of them are open source. Yeah, okay, good. So those are some nice examples, and you know about them. Okay, so this is what I have listed here. Data poisoning, you already know. Model poisoning, some of you said jailbreaking. Yeah, that can be form of model poisoning. So it's like each model has a lot of parameters. Yeah, there are nodes, connections, so according each node there are parameters. Yeah, someone can replace the parameter. Yeah, so if you can get the access of the model, which means you are getting also the access of the parameters, you simply replace the parameters, then model is going to classify some very differently, or it's going to do something else. Yeah, there could be some other thing. So like these days you can see we are using lots of open source codes. Yeah, now we are using open source AI models as well, but these open source places there is not any kind of verifications. Yeah, so but if you consider other places, like you download your apps, right, from Google Play Store, so Google is doing nice checking whoever is uploading an app there, other companies as well, but lots of open source places there is no checking. Yeah, so what you could do, you can take an open source model and you could do some changes in the code. Yeah, and then upload it again, and it can be something that is going to spoil the responses of the model. Yeah, and then basically it's kind of attack on the AI model. Yeah, so attack here doesn't mean like you are going to steal some sensitive information. In a sense it could be like a denial of service. Yeah, so whatever someone expects from the model, that person is not getting that. Okay, so these are some other attacks, I would say, one can think of. There may be more, yeah, but these are the some. Oh, okay. What's this? Okay, I think maybe there is no internet. Okay, it's now there. Okay, anyway, there was a question, so I will go now here. Okay, so how do you think we can oops, let's wait, yeah, this has stopped. So my question there is, how do you think you can stop data poisoning attack? Yeah, so you can think, and you may already see the interface, yeah, in your phone or laptop, wherever you are. So you can type and then you can see. So how to stop data poisoning attack? Can you think of some ideas? Taking data from known sources and not open source sources, yeah, that's good idea. So you basically do things from trusted places, yeah, not just take from anywhere, yeah. Yeah, that's one nice idea. Anything else anyone can think of? Impose access control, yeah, that's one I was going to say in a bit, but nice to see someone has already said. So basically you don't let maybe your model get accessed by anyone, yeah, it's kind of a closed model, yeah. So if it is closed model, someone gets the model, you can put like even ID password or something like that, yeah, and you can allow like nobody can further train the model, it's just whatever it is doing, it will do that. And data validation across the fields, okay, that's interesting. So maybe it's about whatever data, extra one you want to use to train it further, but it is malicious, so that data can be validated, yeah. There could be maybe some filter or some mechanisms before putting it to the AI model to make it basically poisonous. You can have some validation, like how valid, I mean, or if there is anything wrong with the data. If wrong, remove that particular data, yeah. But it can be very difficult job, yeah, not easy. Okay, I think you have nice ideas how to basically stop it. Okay, good. Let me see, I think with this I had a next question. No, this one we have done. Okay, the next one about model poisoning. How do you think we can stop the model poisoning attack? So some of the things you said, it's already applicable, yeah, access control, yeah. Anything else? Black box models, yeah, I think, yeah, that's good. So basically nobody can take it, yeah, it's like a black box, you are never going to get access to it, yeah, or you can never jailbreak it, yeah. So it's closed, you can't really get access of the parameters, yeah, so you can't change it. And there are a lot of models like that, right? The one we use, these popular ones, we can never get access of those, yeah. There was a time, like, you know, everybody started training their own large language models, but then there was also a noise, like if one company can share the parameters with others, they don't really need to train, because everybody is training, like, and this training happens on thousands of servers and over like 6 months or 9 months, yeah, this kind of infrastructure is needed, and the power is needed, yeah. So it's not good for sustainability. So some people raised like if this can be shared, but companies have to make profit, yeah. So they don't want to share. So that is why this kind of thing happened, yeah. So it's kind of black box under those companies' environment, yeah. Okay, I think that's one nice idea. You don't let anybody access the parameters somehow, yeah. Okay. Access control again can be applied, yeah, like in the previous one. Not let anybody access it, yeah. Okay, good. There was third one. Remember I said someone can take the open source code, can do some code re-engineering, can then insert some malicious activities. So how do you think that one can be stopped? So the same thing can be applied, yeah, access control or making it black box. But now I'm saying imagine you get the access, yeah, and then what can be done? Yeah, that's interesting. So it's like if you change something, you want to put it back on the open source platform, you can have some thorough security audit for all code commits. This is what these smartphone companies are doing, yeah. Like if you go Apple Play Store or Google Play Store, Apple, so they basically, you can't just put simply there, yeah. If you kind of put a request, they have a thorough checking. Maybe it's automatic, but if something goes wrong, they send you some kind of email or something. This needs to be changed because they have some security concern. So something like that, yeah. Yeah, but again, this needs a lot of manpower, right? So companies may be not willing to do it, yeah. But this is nice idea, yeah. Okay. So I can think some, okay, so restricted access to only few developers, yeah, you can, yeah, who are trusted basically, you can always try to give access only to those. So in again along the lines of security audits, yeah, so you can perform some kind of analysis on the code, yeah. So it's like there was already a model or this set of codes, yeah, you took it, changed something, yeah, but the one you took, so there could be some mechanisms just to check this is already fine, yeah. Like at the moment you take some executable or something, you try to install into your computer, yeah, but there is some antivirus that checks whether this executable is fine or not, or this application is fine. Similarly, you can have some kind of some checking mechanism, take the code, check it if everything is fine, yeah, and then only basically you let it upload. So there are some people have developed some mechanisms for checking executables, yeah, to kind of find out if there is any problem in that, yeah, and that's what exactly is lots of you can say antivirus things do, okay. So it's some kind of analysis of the code and then coming to some decision based on that, okay. Good. Okay, let's go to the slides now. We did this, we did this. Okay, any questions on this one? No? So with this we have covered basically everything about security, yeah. Now whatever time we have left, we will cover the remaining topics, yeah, sustainability and security together, and we will look what are some emerging trends that we should be typically focusing on in the near future, okay. Okay, so now, oops. So this will be part of these lectures, yeah, 7, 8, 9 and 10. Although for 9 we have partly covered, yeah. So we will focus on sustainability, methodologies and analyzing them and jointly considering sustainability security, and then like I said, we will be looking some emerging trends. So one way to achieve sustainability is basically by doing intelligent computing. So intelligent computing simply means you apply some intelligence and try to achieve whatever you want. So for sustainability we have mainly two goals, yeah. One is when you are doing the computation or something is running, for example this PowerPoint on my laptop, you should take as minimum power as possible. So the hardware should take as minimum power as possible, yeah. So energy efficiency or power is one thing. Another thing is, let's say if this PowerPoint is running, it might be it's heating my laptop a lot, yeah. If it does that, my laptop's lifetime will be reduced, yeah, and then I'm forced to replace. So there is like kind of electronic waste, yeah. So if you can increase the lifetime of electronics, yeah, that's another thing, yeah. So I would say these two things are main. First, that impacts the energy efficiency, and second, that impacts the waste, okay. So basically increase the lifetime and take as minimum power as possible. Again, this is about computing, but there are some other branch of research. I have not done much into that. So it's also kind of true when we get these electronics, yeah, in our hand, and then we start using it, yeah. So when we start using it, then we take some power, right? But there is a huge amount of power that is already wasted in producing it. So if you take a smartphone or laptop, around 60 to 70% power is already wasted. So you use it for next 4 or 5 years, yeah, but by the time you get, because the materials are procured from so many countries, then this is manufactured in a kind of very high temperature environment, and it takes a lot of power there, okay. So it's like lots of power has already been wasted, yeah. That is why you can say increasing the lifetime is even more important, yeah. Then basically these manufacturing doesn't need to happen, and there are lots of, you can say, carbon impact activities can be done, yeah. Okay, so we will not cover something that is basically what can be done before we get the electronics. So we will be looking what can be done after we get the electronics, yeah, and that is part of intelligent computing, okay. So we already have looked the devices at various scales, yeah. You remember there was a chart also. I said these are edge devices, fog devices and cloud, okay. So I'm just putting this picture again, yeah. So we can have devices at various scales, okay, some in the home, some when we are traveling, and there could be some, yeah, like car when we are traveling, and there could be data centers as well, yeah.
What is the difference between edge and fog devices?
So I think edge is typically that we are surrounded with. Fog is called like it's kind of intermediate layer between the edge and the cloud. So it's like some server room maybe in the university, yeah. So first we try to do everything on the edge. If we can't do, we send to fog. If it's still like there is a performance bottleneck, then you can send to cloud, yeah. Okay, so those electronic devices, yeah, those are powered by these kind of platforms, yeah, multi-core platforms. So this one you can see is Intel Xeon Phi processor that is used in servers or data centers, yeah. On the top right you can see this is a board called Odroid XU3, yeah. So that has 8 big cores, 8 big little cores. These are big cores, these are little. In kind of appearance also their size is different, yeah. So it's like one big can accommodate 4 little cores, and then there are some GPUs as well, yeah. So later on we are going to see where exactly this was used, and there are from different companies also, right? From NVIDIA, you know, they have this Jetson series of boards, yeah. So like some GPUs and some CPUs, okay. There are other companies also, they are trying to integrate all different kinds of processing elements, yeah. So these are the kind of hardware or processors that are powering up devices at all scales, yeah. It can be embedded, fog or cloud. And if you look all of these devices, yeah, you can see these three are kind of heterogeneous, yeah. So this one you can see like all the processing elements or all the cores are of the same type, but this one has different kinds of processing elements, yeah. That is why we say heterogeneous, yeah. Like two kinds of CPUs and GPU, so CPU and GPU, and here is like CPU, FPGA and another 16 core processor, okay. So now if we look the one that was on top right, yeah, so that one was actually used in Samsung Galaxy S3 mobile phone. And if you look any smartphone now, the architecture is more or less the same. It's just the, at that time the big was Cortex A15, now big may be Cortex A75 or something. It has become more powerful, and little has become more powerful, yeah. And there is always some GPU. So almost all the smartphones are using similar architecture. So the same chip that was in Samsung Galaxy S3 mobile phone came with some development board as well. So this board is called Odroid, I said earlier, and the chip name is basically the Samsung Exynos 5422 system on chip. So you can say at the end, this is the chip name that Samsung gave it to its products, but it used some processors like Cortex A15 and Cortex A7, but those processors are made by different company, yeah, it's from ARM. So they take it, like they pay for each of them, they manufacture the whole chip themselves, yeah. That's what they do. This big little we already have said. So you saw like there is some heterogeneity, right? There are some big cores, some little cores. So there is some reason to do that, yeah. Why not just have only same type of cores, yeah? So I have put a question here. So what if there is no heterogeneity in terms of processing capability of the cores? So do you think there will be no impact? You can put all homogeneous, or it can impact performance? Maybe I don't need to put that one, yeah, you can simply just talk here. So which one you think is true? Will there be no impact? It will get impact, right? So you know, typically heterogeneity is for a reason, yeah. So the big cores, like I said, one big core, the size of it has like four little cores can come, yeah. So let's say in the phone you are doing lots of things and some more compute intensive processes, then you need the big cores, yeah. But there could be times you basically are not doing lots of things. For example, my phone is sitting idle, yeah. So there could be, everything can be migrated to one of the little cores because that will take very less power, yeah. So basically depending upon the situation or the workload in the system, you have the flexibility to switch from one place to another to save the power, okay. So this big little simply came to basically save power so that the battery of the smartphone can last for a long time. But think like similar approach can be taken anywhere else as well, yeah, like designing the new CPU, designing the new GPU. That is why you say these days anything comes with it doesn't have just the GPU, it doesn't have just the CPU, it has like mixture of both CPUs, GPUs, also some kind of specific processing elements as well, yeah. In the phone these days there is another kind of processing element, it's called NPU, it's like network processing unit, yeah, or neural processing unit. So that does nice job for some AI workloads. Yeah. So there you can imagine now there will be a manager that's going to decide what's going to run, and it's going to decide what kind of processing element has to be used. Okay. Okay. I'm trying to go to the next slide. Okay. Okay. So I think we already have discussed if you have heterogeneous components in your processor, how you can basically make a use of them to save energy. But that is applicable everywhere. Yeah. For example, let's consider the workload of an organization. Yeah. So it's like this whole IIT Guwahati is a processor. Yeah. But the people working and doing anything, they are workload. Yeah. So some of you could be mathematicians, some of you could be computer scientists, coding, and there are lots of admin people, security people, and all those. Yeah. So basically these are different kind of workloads, right? And there will be different kinds of employees as well to handle that workload. Yeah, like heterogeneous. Yeah. So basically, if this is there is a coding job, if you give that to basically some HR personnel, imagine what will happen. Yeah. So you need different kind of employees. Yeah. Just like then these are different kinds of processors that are suitable for different kinds of jobs. Okay. That is why heterogeneity is important. Yeah. So this is how you can allocate different kinds of jobs to the most suitable processor or most suitable person who can do it best. Okay. So like we said, the most important thing is to kind of find out what kind of task to give to what person. Yeah. So that kind of things are also called like some kind of knobs or controls. Yeah. So let's say now we want to optimize something, right? If you're doing that, there is some purpose, right? Either to reduce the cost, reduce the energy consumption, or maybe something else. Yeah. So the kind of controls we are doing, that is called like knobs or control, and we typically can refer that like optimization knobs and controls. Now if we go back to the processor context, we are going to look like what kind of all possible knobs and controls we can have. Okay. So the first one we can say is kind of mapping. Yeah. So it's basically kind of identifying for an application what are the cores that will be used. Yeah. Because in each platform these days, you saw the platforms, right? They are like 60 cores, 10 cores. Which are the cores that are going to be used? So kind of mapping the tasks on the cores. So that is one of the knobs. Yeah. And this is one example. Yeah. So it's like if in your platform there are lots of processing elements, so you can put some task on some cores, and then you can establish the connections. Okay. So here like these 4 cores are used. Okay. So this is one option. Yeah. But you can map, basically you can use any combination. You can use 1 core, you can use 2 core, you can use 3, and out of like 3 you can decide these 3, you can decide these 3. So many possibilities. Yeah. So mapping is one of the knobs or controls if you want to optimize something. And if you are doing all those mapping options, you know the results will be different for the timing, like how much time the whole application will take to execute and how much energy it will consume. Yeah. Similarly, it will apply at a lot of places. Yeah. Let's say in the data center there are a lot of servers, right? If there is a request coming from outside, it depends on which server, in which way you are using the basically the processors, it will have different power consumption. Okay. So mapping is one of the knobs, I would say. Yeah. So we already have seen what it does. It defines the assignment of the task, and also it defines the ordering of the task. When ordering comes into picture, let's say on one of the core there is more than one task, right? And processor will be given to only one of them at one time, right? So ordering is basically which one will be first, which one will be after, which one will be next, or it could also be in a round robin fashion. Yeah. So for example, in our laptop, there are a lot of applications running, right? So there is an ordering defined. Most of the time it is kind of a round robin fashion. Each of the processes are given time, yeah, few cycles, few cycles, few cycles. That's why everything is running together. Okay. Similarly, ordering has to be defined here. But mapping is part of both, yeah. Finding the location, and if at one location there is more than one activity, which one will happen first, which one will happen second. Okay. Another one is DVFS, dynamic voltage and frequency scaling. Yeah, we already have seen it. Yeah. So just to mention, this is supported in many advanced processors, even in the laptop or smartphones, it is there. Okay. So just to brief what it does. So let's say we have this 3-core platform. Yeah. So there will be a controller attached to each processor. Yeah. It's going to basically define if you can run this processor at high voltage and frequency or low voltage and frequency, and that typically you define based on how much workload is there. Yeah. This is again, you can say, to save the power. Yeah. So we can look the example, yeah, how this can be used for energy savings. Yeah. Let's say you want to execute some task, right? And if you are running at the maximum frequency, your energy consumption will be very high from the very start, right? You might remember the equation, how the power is defined. Yeah. So it's like dynamic power is C voltage square into F. Yeah. So if F is high, so it's not like voltage will be the same. If F is high, voltage will also be high. There is corresponding kind of pair, voltage frequency pair. So things will consume lot of power, but it can finish fast. Yeah. But if there is some application, like the deadline is far away, yeah, then basically you don't need to run that fast. You don't need to complete this quickly. Yeah. So you can run at some lower frequency, maybe whatever is maximum, half of that, and then you can take all the time. But if you now compute the overall energy, it might be lower. Yeah. Because every moment you are dissipating or you are taking less power. Okay. So that's the use of DVFS. Another examples could be even if there is no deadline. Yeah. So if my this Teams is running, yeah, or this PowerPoint is running, there is no need to run the processor at very, very high frequency, but you can't also run at the very low. Yeah. Otherwise things can be very slow. So you just have to find the right balance so that you just deliver the performance that is needed, but at the same time you also save energy. Yeah. So my battery can last for a long time, and if this task is running in a data center, again you can save some energy bills. Yeah. Okay. So we saw mapping is one of the knobs, and then DVFS is another knob by which we can control energy consumption. Yeah. Another thing, again very popular, and it has been in lots of processors from a long time, is called dynamic power management. Yeah. What it does, it basically shut down processing elements when inactive. Yeah. So if basically something like a processor was doing something, but maybe after certain point there is no load to process. Yeah. So what it can do, it can shut it down to save the power, right? Again, to shut down the processing elements, there could be two approaches. One could be greedy, another could be timeout approach. So greedy means like the name says, right? Do it as soon as possible. So as soon as processing is finished, go to the sleep. Yeah. And lots of actually in our laptop we can do that. Yeah. You can define the time when you want the laptop to go to sleep if there is no activity. Yeah. No activity means there is no processing, so it can go to sleep. Yeah. And another one could be timeout. Yeah. Again, this one we do in our laptop, right? We set a time. So even if there is no workload, we stay active until certain point, and then we go basically the sleep mode. Yeah. So these are the ways basically to save the power. Okay, and again the same can be applied everywhere. Yeah. Okay, now I have a question. Which approach you think is better, the greedy one or the timeout? Okay, I will throw that slide, not this one. We have done this one. Okay, here. So do you think greedy is better or timeout is better? Timeout is something that we have in our laptops, right? You can say go to sleep after this time, that time. Yeah. Okay, good to see there are people on both. Yeah.
Vary on the application, what kind of application we are using the machine for.
Interesting, yeah. Yeah, so I would say it depends on the situation. Sometimes greedy can be better, sometimes timeout can be better. But there is a reason for it, yeah. So what it is doing, so it's running at high frequency, you can say, then processor finds there is no workload, yeah. Then it goes to sleep mode. Yeah, greedy is going to sleep as soon as there is no workload. Yeah, but if you go in the sleep mode, to come again into the normal active mode, it takes time and it takes power. Yeah, so for example, even the laptop, right? There is like hibernate and all those kind of modes, and shutdown. Yeah, so it depends where you are, and then it takes more time to come. Yeah, it's like a hill. Yeah, if you go more down, it will take more time to come up. So if you have gone sleep, yeah, and let's say you did greedy approach, maybe just after 1 second a workload came in, yeah, and it needs to be executed, but then it will not be immediately executed because the processor has to come to a normal working stage. So the workload will have to be waiting, yeah. So there will be penalty in performance, yeah. Okay. Whereas if it's timeout, maybe you waited like 5 seconds. If this workload came just after 1 second, when nothing was like the previous one finished, then basically it will pick, yeah. There's no need to come again from the very idle or sleepy stage to this one. Okay. So again, it depends. If it's very kind of a dynamic situation where the workload may come at any time and can go any time, so in that case I would say greedy is not the best. Yeah, you can kind of think of, okay, if there is no workload after maybe 5 minutes, it is expected there will be nothing. Yeah, so but yeah, so in that kind of fashion. Okay. Yeah. So it's like you said, depends on the situation. Yeah. So one can perform better than other. So it depends where exactly it's being applied. Okay, it's slow. I think when I'm on this kind of slide, it takes time. Okay, so we saw basically two controls, DVFS, mapping. Yeah. The third one we can think of is kind of partitioning. Yeah. So typically you have kind of this kind of workload. Yeah. The applications are represented typically as data parallel. So that means like there can be many processes that can be happening at the same time. So let's say this is representative of one applications. Yeah. and each of these elements are called work items. Yeah, if you go to GPU programming, this is how it happens. Yeah, so work items are called like in OpenCL programming language, that's for GPU. So if for an application you have this many work items, now if you have a platform that has both CPU and GPU, right, then you have a job to kind of identify what fraction of work items will go on the CPU and what fraction of work items will go on the GPU, right. So again, you can see here there are so many possibilities, yeah, but this partitioning is another basically control, yeah, or knob. So you can define several partitions and each of them are going to give you different energy consumptions and different performance. Okay. So here this is one, just an example, yeah, this is one you can do. So like 0.60% of the workload or 60% of the work items on the GPU and 40% on the CPU. Yeah. So we have seen three of them. Yeah, mapping, like what cores do you use, and if on a core there are more than one task, in which order they will execute. And then DVFS is another control. Third one is partitioning. Okay. I think we will take like 5 minutes break and then we start again. Yeah, it's not a proper break time, but just 5 minutes to relax a little bit. Okay. And later on we are going to see use of these. Yeah. So in my research group, what we did with these kind of ideas. Okay. So how much energy we saved. Okay.
Kind of partitioning and mapping comes together now. First we do partition and then we like map ki kaun sa wala block jo uska execute karega.
I think these all three can come together. Yeah. So because some architectures are like there is a cluster of CPU. Yeah, I said there is another cluster of CPU, another cluster of GPU. So first there is hierarchy, right? You have to define like, okay, how much workload goes on this cluster, and then within the cluster how do you partition, and even if you partition, how, at what voltage and frequency you run those different cores. So there are so many possibilities. Yeah. So that is why if you apply kind of some reinforcement learning or something in these situations, it's never best. That is why you can't find any reinforcement learning or AI based approach in the smartphones. Yeah, because the possibilities are so huge, it's not going to give you the best results. Yeah. Okay.
So what kind of factors will decide the partition?
So I think it depends what you want to achieve, what's your aim. Yeah, if it's timing, you may define like maybe half. If it's energy consumption, maybe this way. In a bit we are going to look basically, if you partition in different way, what is the impact on energy, what is the impact on performance. So then you can decide like what exactly you want to achieve. If you want low energy, you choose this kind of partitioning. If you want high performance, you choose this kind of partitioning. Yeah.
In the performance, it will include latency, throughput.
It's mainly latency and timing. Yeah, latency, timing, throughput. Yes. Okay. I think that clock is slightly different. So just 5 minutes from now. Yeah. It's 10:30. Yeah. Around. Yeah, not exactly. Okay. Okay, let's do next 20 minutes, yeah, 25 minutes. Then we have this proper half-hour break, yeah. So I already have said these kind of things. If you work with any libraries or tools for GPUs, they provide this opportunity. Yeah, OpenCL is one of them. CUDA, you might have heard, is popular for NVIDIA GPUs. They do not say work items; they say something else. Yeah, but it's essentially the same thing. Okay. So now let's look some application domains where those principles, yeah, mapping, DVFS and partitioning can be applied to do some sustainability, yeah, which means kind of improving the energy efficiency or increasing the lifetime. Okay. What are those application domains? So one of them is multimedia applications, yeah. So you know, multimedia is like lots of image processing, video processing, listening to music and all those kind of things, yeah. Again, this has to be run onto some infra platform, and this could be like a multi-core platform, yeah. Let's say if this is our smartphone, right? This is, we saw the architecture, yeah, like the multi-core or many-core architecture that can be in a smartphone, yeah. So this can be inside this, which means if you are watching a video, you are taking a photo, or you are listening to some music, or you opening a browser, so some task will run in some of the cores, right? And now you know, with those options, mapping, DVFS and partitioning, you have lots of choices, right? You need to kind of decide which, if the browser application opens, which core it will use, or if it is a kind of multi-threaded application, which 2 cores it will use, or which 3 cores it will use. And also it's going to compete resources with other applications, okay. So mapping is going to play a lot of role, and if each of these cores supports voltage, different voltage frequency levels, so you need to decide like how much workload that core has, and then decide which voltage frequency it should use, yeah. So in that process you can save power, yeah. So what typically you have to do, like I said, you load the tasks on the resources, and also over the time you adopt, yeah. It's not like if you put your browser maybe on these 2 cores, you should not always keep on the same, yeah. It could be in future there are lots of applications running, then this core might need to be shared by other application. So maybe you need to move things on one core for one application. So over the time, depending upon what is running, you need to adopt, yeah. And when you are doing this, you can try to meet lots of objectives, yeah. Could be the timing, performance, it could be about energy efficiency, it could be like you are trying to balance the temperature of the smartphone, right? And you can also try to meet some security objectives, yeah. Okay. So security one, I think at the moment when you do resource management, it's not done a lot in smartphones, but if you remember I said there are upcoming architectures, they say there is like a secure zone, there is non-secure zone, right? So if there is kind of a like a banking application, yeah, we have lots of banking applications, right? So you can decide those kind of things always run in the secure zone, yeah. So it will have its own memory and everything, so whatever, like the password, everything is cached, nobody else can see, okay, if someone gets access of your device and tries to do reverse engineering. Automotive is another case. Remember we said there are like hundreds of electronic control units, right? These are simply microcontrollers or processors, okay. So these are distributed, and if you remember I said they are connected by a CAN bus, yeah. So again, during different time what the car is doing, there is a lot of tasks going on, so you can decide which task is going to run on which core. In the car there is no dynamic voltage frequency scaling, yeah, everything is running at the same frequency, so only the mapping is the main part, yeah. And in car the most important metric is the timing, yeah, because it's very critical system, okay. it could be applied in server and cloud computing systems as well. Yeah. So how typically servers are designed, or HPC platforms? So you have several nodes, yeah, and each of the node is like a server that has processing elements, and they are connected somehow. And then each of these nodes or servers are managed by a kind of entity called platform resource manager. Yeah. And that platform resource manager is basically kind of running on another server, but that is like monitoring everything, yeah, rest of them. So if that's the situation, then basically it can keep getting lots of jobs from different users across the globe. Yeah, like there are many people who use Google's data center. Yeah, many people are using OpenAI's data center, so they are requesting lots of jobs, right? It's like everybody is typing into ChatGPT to get a lot of answers. So lots of users from lot of places, but then they are going to decide basically from where exactly they need to match, yeah, the answers. Okay. When you are doing that, you can have several aims, right? And one of the aim could be energy, yeah, like reducing the energy cost of the data centers. There is another aim, value. Value is basically the profit or money for those companies. So when they are doing that, this is their first aim, like they want to maximize the profit. Okay. Later on we will see like what it means. So profit typically means you try to complete application as soon as possible. So for us it doesn't matter, but there are like the banking companies or some other companies, they give the task to these data centers, and there is a pricing model. They say if you finish my task in 1 hour, this is the money you will get. If you finish my task in half an hour, you get more money. Yeah. So there's a time and the kind of value curve. It is like this. Yeah. So you take more time, you get less money. You finish fast, you get more money. I think because these banking sites have to kind of decide the next day or within a couple of days next steps, yeah, whatever transactions has happened and all those kind of things, yeah. So you get that kind of money, yeah. Even this kind of thing can be used basically for like the social media companies, right? They look for a lot of users what you are doing. Based on that you get some ads, right? Sometimes you have accessed something, you get some ads, yeah. But these companies are not doing just for one person at a time. So they're taking whole data from all the users, and then they are trying to analyze all the data and throwing you the ads, yeah. So similarly this can be done. Throughput is again like how many applications you can finish within certain time. So the aim is always to get the highest throughput, yeah. I mean there are some research where people have tried security optimization as well. Again, kind of defining like some of the servers are maybe more kind of handling more sensitive workload, yeah. So putting the workload into that, okay. Okay, now I have a question. Can you think of any other application domains where you can apply similar kind of optimizations? Yeah, it's basically mapping, DVFS, and partitioning. Yeah. Okay, I think I need to switch to that screen. So we saw multimedia, the cloud, and then automotive, yeah. Anything else you can think of? Do you see it? Okay, I see it now. Okay. No? I would say like wherever you have a processor, yeah, and there is not a single microcontroller, you have more than one, yeah, and if some of these or each of these support this dynamic voltage frequency scaling, yeah, so it can be applied any of those places, yeah. So those three I said you mentioned, this is the kind of application domains I have considered in my research, but there could be many others as well, yeah. For example, it could be like some kind of in medical field as well, yeah. Let's say they want to discover some new drug or something. I told you the example, yeah. Or some people are taking lots of images of something that, I mean, imaging is one of the ways to drug discovery, yeah. So what they do is like they put some tissues, they put some kind of you can say chemical on the tissue, then over the time they observe what kind of changes are happening, and every second they take like hundreds of images. There are like high speed cameras, and then these images are going into a computer and then they process. So again, if the application is coming from medical domain, but the platform at the end is this, then basically the same thing can be applied, yeah. They have like millions of images, then again you have to decide on which server which one should be going, and then how they will be processed there, okay, yeah. So medical is another one. Manufacturing and control systems again could be interesting. So let's say in manufacturing you have again lots of microcontrollers at different places, yeah, to monitor or to take some actions. So depending upon what it has to do at different points, again if it supports like different power modes, you can make it up, make it down, yeah. Maybe there's a manufacturing pipeline, right, and there are so many stages. At the last stage maybe nothing is going, or something will reach after 1 hour, then you need to turn those electronics. You do not need to turn those electronics, yeah, until things reaches there, or it needs to be processed, yeah. Okay, good. So medical, manufacturing, yeah, these are other two. Okay, now these the things we are doing, right, these controls, in a way we are trying to optimize something, yeah. We are doing it to optimize timing, energy, or security, something else. And if we take these methodologies that basically exist in the whole literature, we can classify them into two categories. One thing we can say is design time, and this one is for a static workload, yeah. Another one we can say is run time, that is for more dynamic workload. So static workload is like, you know, this is the application, there will be no other application that is going to run, yeah. So for example, in a smartphone, yeah, remember long back, you could only call, yeah, you could only just play few games, maybe snakes, ladder, those kind of things. You knew there are just few applications you can run, yeah. So that is a more static scenario. Now it's very, very dynamic. But if it is static, you kind of know what is the platform, what is the workload. You can do the optimization in a different way, yeah. But if things are changing a lot, those things will not be applicable, yeah. So now we are going to look some of the design time optimization approaches from the point of view, again, we want to touch sustainability, so we want to reduce basically energy consumption, okay, and then we will look some runtime, okay. Okay, so for design time, so like I said, you know the whole workload, you know the whole platform, yeah. So you can perform optimization with a global view, yeah. So it's like, you know all the situations, you can find the best mapping or best operating DVFS points or best partitioning, yeah, because there is no other application that is going to come. So it's always the same, okay. And this one will result normally in a better quality of results, yeah, because in comparison to runtime, that where the situation is always changing, so it's not easy to get the best results, yeah. And there is a huge literature that falls under this design time optimization categories, okay. So let's look some of these literature. So these are literature are also kind of classified into different well-established search approaches, yeah, like simulated annealing, taboo search, integer linear programming, genetic algorithm. There are many others, yeah. Out of these, so you can think like, let's say you have a phone and then there is a task like multimedia, and that task may have maybe 10 processes, yeah, and then your phone has 8 cores. So those 10 processes has to run on 8 cores, yeah. Again, there are so many possibilities, yeah. You can use 1 core, you can use 2, you can use 3, but if you're using 2, which 2? If you're using 3, which 3? So many possibilities are there, yeah. So to kind of discard some of those possibilities that may not give the best result, you know. So there are some approaches called like pruning, yeah, so that you can get the best solutions or best operating points as quickly as possible. Otherwise, sometimes it may take like whole month if your, like, let's say in your platform number of cores are 1000, yeah, and if you have like 10 applications each with 10 processes. So there are approaches that apply pruning approaches, yeah, pruning strategies. So simply means you don't need to evaluate all of the possibilities, okay. That's a way to discard some of the possibilities. Okay, I think I have a question after this. So do you see any disadvantage or disadvantages to prune the search space? Okay, let's see this view. No? Good. The good part is you can get the best solution in less time, yeah. And I do not have much time, but in one of the our research we have shown like you sometimes need a month to, if you are exhaustively exploring all the possibilities, because possibility simply means take the task, put on the core and evaluate how much time it will take and how much energy it will take, yeah. Then do the same for other possibility. And again, each of these possibilities you have to also evaluate. A core is running at certain frequency, yeah, another frequency. Evaluate all these possibilities, and then that takes a month or something, yeah. May not give 100% accuracy. Maybe you want to say efficiency, yeah. So it could be, if you are pruning, there is a possibility you can basically discard some of the points, might be that one was good, yeah. So it can happen, yeah. So that means less efficient, yeah. So there is a possibility you can miss some kind of nice points in this process, yeah. But like I said, you cannot explore all the design space within a limited time, so this is typically a practice, okay. So I would say there is some disadvantage, yeah. You may miss some design points that are useful. Okay, so I am just saying here one example of like exhaustive DSE. Exhaustive means evaluate all the possibilities, yeah. So now let's say like your mobile phone, yeah, you need to run maybe hundreds of applications, yeah. You take your architecture, that is the chip that is in your phone, and you take the exploration matrix, like what you want to achieve, yeah. Maybe you want to take less energy. So for each of applications, you will try to find lots of options, yeah. Like there are a lot of possibilities to use different kinds of cores, and there, if there is GPU, it can be partitioned as well. So even just for one application, this can be millions of possibilities. Similarly for another application. So imagine in a phone, if you want to do for hundreds of applications, this can be billions of, many billions of possibilities, and you cannot evaluate all of these, okay. That is why the pruning is applied, okay. All right. What's the time? Should we break now? Oh no, we have 2 minutes more. Let's look this one. So if you remember, I said there are well established search approaches, right? Tabu search, integer linear programming. I also said about genetic algorithm. So this one is very, very popular, yeah. So you can say genetic algorithm is again like bio-inspired approach, yeah. So we are going to look this with an example, and we will look these two aspects, basically mainly these two controls, yeah, mapping and DVFS, okay. And the example that we will look is this autonomous, not autonomous, but automotive vehicle, yeah, basically a car, yeah. So we have already seen something like this, like a car has several electronic control units, and here it's about more detail, like these electronic control units are distributed across different sections, yeah. One is powertrain system, safety systems, and comfort systems, yeah. And these are again in 100, yeah, like 100 to 200, okay. And out of these, the engine control unit, yeah, is the most complicated electronic control unit, and this belongs to powertrain system. So basically the electronic control units that are near the engine, okay. So we are going to basically look the tasks typically that are running in the engine control unit system, okay. So here I am going to show a kind of demo car example, yeah. In a real car there will be so many tasks, yeah, maybe thousands or maybe millions, yeah. So this one demo car is minimal functionality gasoline engine control unit, yeah. That means this is like a toy car, yeah, it's not a real car example, yeah. So you can see this is a complex graph. So in the engine control unit there will be like, these are the tasks with the squares, yeah. So these are the tasks, and when they are running they will exchange some messages from others, yeah. So here you will find like there are total like 18, actually in automotive terminologies these tasks are also called like runables, yeah. It's just the domain change, things change. So there are 18 of these boxes, yeah. That means 18 tasks are running, okay. Automotive, like I said, these are called runables, and task definition is slightly different. So you can see some of the runables are with the same color, yeah. So essentially they are doing more or less the same task. So it's like for one task there are two processes, yeah. So the runables can be processes here, okay. So 6 colors you can see, okay. And there are 61 labels. So those are basically just the edges, yeah, the way where they are communicating. So labels is called like, let's say there is a need of communication from here to here, so there will be a buffer or something, yeah, to hold the data, okay. So this is the demo car example with 18 runables, okay. Now what will be the design time DOC? You want to take this kind of application, yeah, with 18 runables, and you want to take a multi-core platform, yeah, these are like 6 cores, and then you want to map on this, but again like I said there is huge possibility, yeah. So you can do some design space exploration to come up the best with the best possibility, or some couple of them, yeah, to decide on which one is the best, okay. And when you are doing this DSE, you are trying to come up with the possibilities. One thing is you can do exhaustive, yeah. evaluate all of them, but that's not possible with the limited time. So when you are going to come with some limited set, you have some aims. Yeah, what could be? It's like you want to find all the possibilities. There is no deadline miss, because car is a very critical system. Yeah, like I said, brake has to be applied within microseconds, so that deadline should never be missed. Okay. There could be some other goals. You want to use minimum resources. Yeah, it's again for sustainability. Yeah, and you also want to reduce the energy consumption. Yeah, so if it's car, basically, now if it is EV, you can enhance the lifetime. Yeah, like you don't need to charge the battery again. If it's data center, again you are reducing the energy bills. Okay, so this is what basically can be the goals. In the next one, I am going to kind of explain how the genetic algorithm can be used to get the best design points, yeah, by which we can operate. But before that, let's have this break, yeah, half an hour. Okay, good. I think there should be some tea or snacks like yesterday. You can check, yeah. Okay, can you hear me? Okay, good. So like I said, we are going to look basically something that is called genetic algorithm, yeah, to explore the design point, and this could be the goals, yeah. And for sustainability, we want to minimize energy dissipation, okay. But before we go to that, I wanted to introduce something that typically happens in a car. So before we look this one, let me try to explain something like how the car operations are defined into different modes, yeah. So it's like when you want to drive your car, first you go near it, right, you unlock it. So that's like one of the mode of the car, let's say mode 1. You unlock, few electronic control units start doing something, which means those runables, we said 18, right, that's very toy car, yeah. So some of the activities starts happening in some of the electronic control units, which means some runables starts running. When you go in the car and do maybe not start the engine but turn the ignition on, then there are more electronic control units doing more tasks. It could also be it's the same task or same runnable, but they are running more frequently. Previously they were maybe running once in every second, but now they may run like 50 times 1 second. So their period changes, yeah. And then when you start the engine, that's called like cranking, then you're like more runables run in different electronic control units. Again, it could be the frequency of runables may change. Again, when you like start driving, then the state again changes, and in driving as well, it could be you are driving at low speed, that's one mode. Then if you are driving at high speed, that's another mode. In all these modes, there are runables running in different electronic control units, yeah. Okay, so that's kind of a way to define the state of a car, okay. So this is another way to define the state. I think this one is defined by Infineon, yeah. So they are kind of major software developers for automotives. So they say there could be kind of power down mode, that means nothing is happening. This power up mode, the car is running, is stalled, like you were driving but all of a sudden you stopped it, yeah. Cranking, we have seen it. Idle, like maybe you are waiting at the traffic junction, yeah, and you are driving, okay, and then there is some wait, okay. So like I said, runables behave differently depending on the state. So in some state they may run more frequently, in another state they may run less frequently. So now you can see there is a lot of states, right, and if you are driving your car, if you are changing from one to another, it might be so much changes, yeah. So that means you need to switch from one mapping to another. So runables need to be distributed always in a different way. So some companies propose like we can cluster some of the modes, yeah. So it's like power up is there, and some modes can be clustered into cluster 2 and some in cluster 1. The reason is then you don't need that much switching, yeah. And another is the modes in one cluster, they are also more or less similar, yeah. So it's like if you are, let's say, driving from 0 to 20 or from 20 to 40, there is no need for two modes, yeah. They all can be combined because behavior is more or less the same, okay. So like I said, this is to avoid this context switching a lot, yeah. And some of the neighboring modes, like I said, they are quite similar, so no need to have separate modes. Now we will see like how we can apply genetic algorithm for one of the modes, okay. So anyone aware of the genetic algorithm? Have you used, have you heard? Some of it, yeah, okay, good. So maybe I will just quickly brief, yeah. So what do? You take your application model, you take your platform architecture, yeah. Application model means like how many tasks it has. So you saw we have 18 runables, yeah. And platform architecture, like what is the architecture on which those 18 runables are going to run. Okay. And with those application and platform, you create some initial population, which means let's say maybe 10 mappings. Yeah, those 18 runables, if it is like on a 4 core, there are so many possibilities to map. Yeah, maybe all on 1, distributing on 2, distributing on 3, this way. You basically generate some initial population. It's like initial design point, and then you evaluate all of them. Yeah. So evaluation can again mean like what you are evaluating, maybe energy consumptions or their timing. Yeah. And then from those initial populations, you do some selections. Yeah. To choose maybe 2 of them, and do some operations like crossover is one popular operation. Another is mutation. Yeah. So you can see in crossover, it's just like something, one particular kind of mapping, or like one task is moved from one place to another. Yeah. In mutation, it's like more. Yeah. You can read more details there. And then you get a kind of new design. Okay. So then this one is called offspring population. After that, what you do, you take those initial ones and then the new ones that you have produced and make a combined population. Okay. And then from these combined, you choose the elite groups. That means the one that are giving the best result. Yeah. So it's like, let's say initially you started with 10. Here maybe you got one more. Then out of these, you just choose 10. Yeah. So basically discard the one that is not the best. And then these the best ones or elite ones, you make the initial population. Again, choose some, do these things, you keep doing. Yeah. And after some time, you will find like these ones are the best ones. Yeah. So this is how you can say genetic algorithm is applied. Okay. And here we will look like how this can be done for power up mode. Okay. So I hope the concept is clear. Yeah. And this can be applied forever. Yeah. Unless you have explored everything. That is why when you are applying genetic algorithm, there is something like number of iterations that you want to do. Maybe you want to stop after 100 iterations. Yeah. It's like training epochs. Yeah. How much time do you want to do? Okay. So like I said, in the fitness, you can set some criteria. Yeah. So basically you want to reduce the energy consumption because of sustainability goals, and you can put huge penalties for deadline miss because it is safety critical system. So if you are doing that, your basically the elite group will be trying to choose the population that will try to meet those goals. Okay. Now in the genetic algorithm, there is something called genes, right? That's how the name has come. So don't look the top one, we forget the top one. So you know we have like 18 runables, right? So let's say these are the tasks, yeah, or processes, and that need to be mapped on the electronic control units. Yeah, let's say these are the electronic control units. Yeah. So these runables has to be mapped on it. So this now has to be the platform, and the application has to be represented into some gene format. Yeah. So what we do for each runable, basically we take one gene. Yeah. So let's say if we have n runable, we take n genes. Okay. And how many cores we have, we take that many extra genes as well. So if it is like x by y, so we take x into y genes for the cores. We are doing these things because here with these ones, we are going to explore mapping, and with this one, we are going to kind of find out the best power operating mode or best DVFS point. How this will be done? So like in this one, basically you can put like runnable 1, yeah, and you don't, so kind of this is each representing runnable, right? So here if you have to find the mapping, you have to find out where the runnable 1 is going to be mapped, yeah, where runnable 2. So inside each of these you can put the core, which core on which on which core number it is going, yeah. You can say this pi 1y, yeah. In the second one also you can say pi 1y, which means runnable 1 is going on 2 cores, yeah. So this is like how you can define the mapping. And in this one, like this is all different cores, so you can decide what are the power modes, okay. So you can see just with combining some genes, you can define the mapping and you can define the operating voltage frequency as well. So now you remember in the previous slide, we start with some initial population, right? So this is one of the population. Similarly, you can generate more, maybe 10 of them, and then apply that process and keep repeating the process. After certain point, you will get some points, or you can choose the best gene that will say, okay, what is the mapping, yeah. So that means what is the core number inside each of the runnable genes and what is the voltage and frequency, and then you can choose the best design point, okay. So this is how it can be applied, okay. And we applied this for automotive car. I think we, in the genetic algorithm, we do like hundreds of iterations, yeah, and then we stop because that already takes like 7-8 hours to do it. So that's why we have to stop. Okay, now I have a question. Let's go to that interface. Not yet. Not yet. Oh, have we gone back? This one. Okay, some of you already answered. Okay, it's always good to see responses at both the places, yeah. So will you always get optimal design point when using genetic algorithm? So optimal means the best, yeah. There cannot be anything better than that, yeah. Yeah. So if you want to get the optimal, there are ways. One is exhaustive, right? You explore all the points and then just choose the best. But having 18 runnables, maybe 9 cores, it's going to take so much time, yeah. It won't be possible to do exhaustive search. So there is a possibility you will not get the optimal point. You will get the best or the most efficient, but you may not get the optimal design point, yeah. So if you are working into this kind of field, like exploring the design space, there's always a question like how far you are from the optimal, or some people say like oracle solution. That's like somehow you get the best, like exhaustive search, yeah.
Isn't the most efficient the optimal one?
Yeah, it's most efficient. No. So if you're doing some explorations, right, that will give you something that is best, but that may not be optimal. I mean, you might have missed optimal in exploring the whole space. So optimal is something, there's nothing better than that.
Better in terms of efficiency, right? Isn't efficiency what we are going for here?
Yeah, it's efficiency. Like let's say the one we want should have minimum energy consumption, yeah. So it could be you can find, but it's possible you will miss it as well, yeah, because you started with some population, right, and then you are going further. So it's like humans, right, because this genetic algorithm is like human reproduction system, yeah. So I mean it can be always better, yeah. So the thing is, you may find, you may not find, yeah, okay. But it's kind of just a chance. So it cannot be proven like you have reached the optimal design point, yeah. That is why if you apply genetic algorithm, any like kind of pruning, everybody will ask you how far you are from the best or the optimal. But in some situations you can't really find the optimal, yeah. So in that case, you just have to say something in comparison to what research has already been done. You say, okay, I can perform my search in less time, and the solution that I get, it has better energy consumption or kind of lower energy consumption in comparison to existing approach. Yeah, okay. So yeah, so you may not get always optimal design points. Yeah. So the thing is, if you have like maybe less number of cores, yeah, your gene size is small, that means less runables, less cores, it might be possible. Let it run for maybe a couple of days, then you may find the best, the optimal, but not if there is huge possibility. Okay. So yeah, if you get a question like that say no. Yeah. It always is stuck when I use this interface. Let's see. Okay. All right. So I'm not putting some results because I wanted to cover some more things that you may find interesting, but these are listed in this paper. Yeah. So also this work, now I'm not focusing at the moment. I'm trying to apply now genetic algorithm in some other domain, but this was for automotive domain, and we got the paper published, but others we have not published yet, so I have not covered. Yeah, but same can be applied other places as well. Okay. So now let's look the partitioning. Yeah, we covered another aspect, partitioning. Yeah, so in a specific we are going to look the partitioning between CPU and GPU. Yeah, so if you are partitioning, it's again design space exploration. Yeah, it's just to find out what fraction of workload you want to put on CPU and what fraction you want to put on the GPU. Okay. So this slide you have already seen. Yeah, this is just one example partition, like 40% of the workload on the CPU and 60% on the GPU. Yeah, but there could be other possibilities as well, right? So in one of the experiments, so what we did, basically we took 4 applications. So this is like SYR2K, SYRK, correlation and covariance. Okay, so I think these are from Parsec benchmark or its modified version for CPU GPU workload, and we measured execution time, that is shown by bars, and the energy consumption, okay, that is shown by lines. And here on the x-axis, it is about the fraction of workload on CPU cores. So it's basically defining how much will be on the CPU, how much will be on the GPU. So if you say fraction of workload on CPU cores is 0, that means everything is on the GPU. Yeah. If fraction of workload on CPU core is 1, that means everything is on the CPU, nothing is on the GPU. Yeah. If you come like 1/2, that means half of the workload is on the CPU, half is on the GPU. Yeah. So with this you can see different partitioning is giving you different timing results and different energy results, right? And with this kind of graph, you can also see some applications are running well on the CPU, right? So you can see this red bar, right? That is correlation. If the fraction of workload on CPU is 1, yeah, like everything is on the CPU. So the timing is like, I think if you go here, like maybe 50 seconds, yeah, or 55 seconds. But if everything is on the GPU, that takes more than 120 seconds. So it could be there are some applications, they are not the best on the GPU, they might be best on the CPU. Okay, so this is the first point, yeah. But if you look in general, the timing is somewhere best here, right, lower, and even the energy is somewhere kind of lower in the middle. That means it's always good to partition, but you need to find out which one you choose. Yeah, So I think if you want to kind of take care for both timing and energy, so you can think of, you want least time, you want least energy, right? You can multiply these two factors, and the one that the partition that give you the least of the value, when you multiply both time and energy, you can choose that, yeah. But if your energy is more important, you just should look that, yeah. If your timing is more important, you can look that. Again, think like we have done partitioning not at very high granularity, yeah. This is like only eight of them, yeah. You can think of even 100 ways, yeah. So it's like 1/8, then like that's the smallest, yeah. But you can think of the whole workload, maybe 16 partitions, yeah, maybe even more, 32 partitions. Then this design space can be even huge, yeah. So this is how you can explore the kind of partitioning results, okay. So that's all about design time optimizations, yeah. So here it's like, if you know the workload, you know the platform, you can find out what could be the best mapping, what could be the best DVFS points, and what could be the best partitions. Because you have a lot of time to explore, you can do it, okay. Now the next thing I said, the whole management, resource management can be also in the form of runtime optimizations. So this is the kind of situations where things are changing a lot, yeah. Like I said, in our smartphone, different applications are running at different times. So then design runtime is better typically, okay. How this is done? So in all the device, we typically have this 3-layered architecture, yeah. So at the bottom there is a hardware, yeah. Again, we have seen some hardwares. These are like hardware resources, maybe some CPUs, some GPUs, and they also support some voltage frequency labels, yeah. And these hardwares also have something called performance monitoring counters. They have different registers, yeah. Different things are logged into that. You read them and then you basically find out, yeah, like how many instructions per second are being executed. Or sometimes there are sensors into that. You can get the power, you can get the temperature, all those kind of things, yeah. And the top you have applications, right? And these applications again can be multi-threaded, so like there are many processes into one application. And they might also have some requirements, yeah, like you don't want to take too much time to run an application, yeah, or you don't want to waste a lot of energy for an application. So these applications have to go on the hardware. But typically then in the middle we have something called like runtime management layer, yeah. So this is typically in the operating system. There is a module that decides how things are going to be mapped, or where things are going to be mapped, and how this will be running, okay. And this module that decides this kind of arrangement, it's called like operating system scheduler, yeah, or power governor. So there are two entities. Scheduler is basically deciding thread to core mapping, so where things are mapped, and governor is going to decide at what voltage and frequency the cores will be running, okay. So now you can see again, this has a complex job, yeah, because there are so many resources for each application. So now when it's performing its job, it has to address so many challenges, yeah. Coming to sustainability point of view, if it could be like if one of the, I mean, so it's like there are many cores that the application may need, right? But if lots of applications are running, it's difficult to find out which one to allocate to which one, right? And here some cores may heat up excessively, right? Maybe one core is being used a lot and it may fail. So we have to find out how to keep them cool, yeah, or how to work around it, okay, to make the chip last longer, yeah. So this one we have covered. Again, if there is one application or two applications, it's not that difficult, right? Because there are so many of them running at the same time, so the job becomes difficult, okay. Again, You remember, like we said, that these architectures these days are becoming more and more heterogeneous, right? There is many types of CPUs and GPUs as well. So that makes this kind of scheduling or governing decision even more difficult. Yeah. So these are the kind of research questions that this particular component has to address. Okay. And if we look like from sustainability point of view, we want to care for energy and reliability of the system. Yeah. So reliability means it's operating in a reliable way, and also it should last for a long time. Okay. So these are the two metrics that we can look. Okay. Now these approaches, I mean, they are called runtime management, and some people refer it as like dynamic resource allocation. So dynamic means runtime, yeah, and some people also refer like adaptive, yeah. So these can be categorized into two main parts. One can be for like hard real-time system. So you know these are safety critical systems, yeah, where timing is very important, like in aeroplanes, in cars, yeah, some other places. Another is called like soft real time or best effort systems. So that are like video streaming is an example for it, yeah. It's like if your TV becomes slow, or if you're watching something it becomes slow, it's not going to cause any kind of consequences, yeah. So you can basically cope with the degradation in the performance. So that is like soft real time. So there is a timing requirement, yeah, like we want the video to be smooth, but if it is not, it's fine, yeah. So that is why it's called like soft real time. You should meet, but if you miss, there is no consequences for it. Here there are two categories. I think we don't have time to look into that. In soft real time, there are again lots of categories: market inspired, bio inspired, non-guaranteed admission control, and congestion avoiding. Okay. So out of these, I think I will cover these two: bio inspired and congestion avoiding briefly. But if you want to look all of them in details, even the comparison results, that is in this paper, yeah. Or I think this was a tutorial or something. So it was presented in that tutorial as well. Okay. So like I said, congestion avoiding is one of the I wanted to cover, right? So let's say if your application is in this format, right? I am saying this as a task graph, but you can imagine this is just a multi-threaded application, yeah, any application. And if you have this kind of architecture, what you will try to do, you will apply best effort to map computations and communications, yeah. So you can see T1 to T4, they are mapped in some way, yeah, and what this best effort should try to do. So it should try to avoid congestion, yeah, and congestion happens when things start talking, right? So you should try to kind of as less congestion as possible. So how you can do that? So congestion doesn't mean like only when things are communicating, because if you put lot of tasks on one place, then also it is a congestion, right? So to minimize that, you can try to homogeneously distribute loads of the tasks, yeah. So try to use as much as resources possible, yeah. And for links, communication overhead should be minimized. So it should not be like you put T1 here and put T2 here, then it has to talk a lot, right? So they should be put close to each other. But you can say, if I want to minimize my communication overhead, I may put all of them onto one, right? Then it's very fast communication. But then the load is too much, right? So we need to find a balance, yeah. So there are some approaches kind of finding out how much workload this one will impose, how much this one will impose, how much this one will impose, how much this one will impose. And then you can find the kind of right balance by distributing it into a couple of sets and then put that onto the cores. And when you are putting, you can think of the reducing the communications, yeah. Don't put the ones far away that they need to communicate, okay. So this is congestion avoiding, okay. And the same can happen everywhere, yeah. Like in data centers, in servers, it applies everywhere. Okay. Okay. Maybe I have already given the answer to this question, but the question is, will it be better to map all tasks and edges to one core to reduce congestion in the cores and links? So you said previously we mapped this way, right? Now I'm saying, if you really want to reduce the congestion, why not map all of, oops, why not map all the tasks onto one core? So do you think it will be better to do that? No? Okay, let me hear your thought on those interface. Not yet. If you can try to give your answer like yes with the reason and no with a reason. I think we can also speak. Typically I am keeping this because we have sometimes some people online. Yeah, I think we don't have many, but sometimes we have. Yeah. Also, if you prefer typing and not speaking, it helps. Hope you can see the interface. Yeah, yeah, I see it. Good. So no, it will cause overloading. Yeah. No, because the other cores will be idle and there will be no use of them. No, as the trade-off is not worth it. Inter-core communication latency is much lower compared to the time we will lose by putting all the computation in one core. Okay. I think most of you are getting it. Yeah. So remember, like, if you could put everything on one core, there was no point of multi-core systems. Yeah. So multi-core came in because then you can distribute and do the things faster. Yeah. So this is similar to like long back we used to get this what is that we cook on food on, like the gas, right, with only one burner. Yeah, people thought, okay, making the burner as powerful as possible to cook fast, but then you have to cook so many things, there's so many workload. Yeah, and then people thought, okay, let's have 2, 3, 4, 5 burners. Yeah, and I imagine like previously there was 1, then 2, now I see 4 and 5. So it's like more and more, so you can perform things in parallel. Yeah, all of them are on, so you finish in much less time. Okay. So same here, if you put everything on one, there is no congestion in the link. Yeah, because they can talk through the shared memory on the same core, but it will take long time to execute because that core is going to kind of do some kind of ordering of the tasks. Yeah, so it will take more time. Okay, so not worth it. Yeah, so both load on the cores and load on the links should be kind of minimized or balanced. Yeah, we have not talked much about links, but it could be also sometimes like maybe this link is being used too much. Yeah, maybe there are like lots of communications, lots of tasks want to talk. So then in that case it might not be better to put T1, T2 here, maybe put T1 here, T2 here. So that one can talk independently here and this one can talk independently here. Okay. So these kind of things needs to be looked. Okay. All right. Okay, this one takes time to move to the next slide. Okay. Okay, another thing I said, we will look is this bio-inspired approach, yeah, reinforcement learning. Again, anybody knows this reinforcement learning? So this can also be used to do kind of some resource management to again reduce the power consumption. So we reduce the energy bills and related costs. Okay. So what typically happens in kind of this reinforcement learning, you have some kind of environment, yeah, let's say earth, and also you have an agent, yeah. So this agent basically observes the environment. So in what state this environment is. So that's the first step. It observes the current system state, and based on the state it selects an action, and that action will be applied to that environment, yeah. And if you are doing that, basically the state will be changed, yeah. And if the state is changed, it will lead to some kind of good, something good or something bad, yeah. So if it leads to something bad, basically then it can kind of observe the state again, then it may select different action, yeah, unless it gets something that is more useful. So this is how you can say the reinforcement learning works. So it keeps trying unless it keeps finding better, you can say, design point or better system state in which it wants it to be, yeah. So now similar concept people have applied onto this when you want to run the workload onto the processors, okay. So something like this. So you have the hardware like your this environment, yeah, and you have your learning based algorithm, that's like basically a brain agent, yeah, that's like in the scheduler of the processor. So here from the hardware you can get some feedback, yeah, like I said there are some sensors, you can get temperature, power, and you can go get some other values from some registers. It's called like performance monitoring counters, yeah, like how many instructions per second are happening, what is the CPU cycle, or what is the utilization of the hardware, yeah. Utilization you can always see in the CPU, right. So based on the state, basically it defines some action. Action could be, if this is a task graph, changing maybe it to from core 1, core 2 to maybe core 3 and core 4, yeah, and then looking like with the changed state whether your performance or energy has been better or not, yeah. If not, again kind of apply some different action, yeah. So it keeps doing this unless it finds a point it is happy with it, like okay, I'm getting better results in terms of energy or power, okay. Now you can see like this is like a kind of is trying to optimize over the time, but if your workload change is very, very dynamic, it might not give you the best results kind of maybe after until 1 hour or something, yeah. And if you again something changes very drastically, it has to again learn the best thing to do, right. So in some situations it might be good, but it again expects the workload not to keep changing a lot, okay. Okay, again a question. So do you think there is any problem with reinforcement learning approach? Okay, let's go that one. I think it looks very fancy, right? Feels like it can give you the best result in all the situations. Even people have applied. But like I told you previously, in our smartphone, there is no reinforcement learning basically to manage the processor cores for the applications we run. Yeah, training time. So basically you're kind of finding the point when you are satisfied, it can be long, yeah. Yeah, it kind of lacks the feedback mechanism. It's just kind of trial. It's trying, yeah. May take more overhead to find the optimal state. That's correct. So you see, you are putting this extra algorithm, right? It has overhead. You are paying for energy cost for it to run. What if it doesn't find anything good after some time? Yeah, even if it finds, maybe that application is going to run maybe 1 hour, right? But it finds the best point maybe just at 50 minutes. So then only for 10 minutes it's running in the best way. But this 50-minute, this reinforcement learning algorithm is extra software, yeah, extra overhead. So we have to kind of find out in what situations it can be good. Okay. So I would say there are some other problems with it. It's not very scalable. So imagine like you have lots of cores, yeah, and if there are a lot of cores, and it could also be the cores are now heterogeneous, yeah. So then it has to basically keep trying for a long time to really find the best solution. Okay, so it's kind of not very scalable. So it again wants like a bit of more static situations, yeah. For Earth example we gave might be good, yeah, because there are global warmings happening, so things little bit are changing. So you can apply some actions, like you can plant trees. Those are the actions, yeah, and then observe what has happened to the planet. It's slow process, slow moving, but in our systems things are moving very fast, yeah. So not the best in kind of very dynamic situations where there are huge number of possibilities. Okay, yeah. I think you can search on my web page. I'm not going to in the details of like how we have exactly applied into some kind of real systems. This one we applied on a smartphone. It's not the best in comparison to what already exists, yeah. So at the moment in a smartphone, most of this is based on utilization. So like what is the utilization of different cores? Based on that, the workload is switched from one place to another. Because utilization is just one entity, and that gives very right kind of measure of the workload, yeah. So it basically still gives better results. Okay. Okay. What's happening? Just give me a second. Nothing moving. This one can help. It is on. It's hanged. Okay. Okay, now it's working. So now I want to introduce some work. It's again is on intelligent computing. Yeah, again, intelligent computing means finding the mapping in the best way and finding the voltage frequency points or finding the partition. Yeah, so that your energy consumption can be minimum. Okay. So first we will look for like a small scale system. A small scale, I mean this could be simply the smartphone. Yeah. And then we are going to look for like a bit large scale system like on a server, and then how we can do the same onto the data center scale. Okay. So I will just try to brief these works. Okay. So you can get the idea. So one of the work again is by a PhD student who has proposed is like called adaptive DVFS. Means like over the time, depending upon the situation, you keep changing the voltage and frequency so that you take basically less power, yeah, and at the same time try to meet the expectation of the smartphone users. Okay, so these are the same blocks, yeah, you can see. Now in the middle where we said there should be a component that kind of maps this on the hardware, he proposed his own approach. It's called like QARM, yeah, I think I forgot the full form. It's like quality aware something, yeah, quality assurance, something like that, resource management, yeah. So how it works? So I mean, this is just with respect to smartphone. So first it predicts something called like TP. So it's like the time when you are going to plug in your smartphone for charging, okay, and then like how much energy you need for that. So ED is energy demand and TP is the time when you want to plug in. So this research was done only with the aim, like we all are here, right? It might be you will go to your hostel or room maybe at 5 or something. So you can kind of, this is prediction is you will plug in your phone at 5 p.m. yeah, but you can check like what is the battery level of your smartphone, yeah. From there you can think of like whether it's enough or not and to last until 5, right? It depends what you're going to do with it. If you're going to use a lot of applications, it might not last for a long time, yeah. Based on like what you're going to do in the next couple of hours, it predicts the energy demand, like how much energy will be needed until you plug in your smartphone based on your behavior, yeah. So some people use the phone a lot in the afternoon, so that kind of behavior is taken into account. So when you are going to plug in and what kind of, how much energy is demanded or needed until that point, okay. So that is predicted, and this keeps happening after certain time, yeah. You keep predicting because things keep changing. And then you do some update of the model. It's with respect to energy remaining and energy demand. So at first this update doesn't happen, yeah. It's like after some time, yeah. So let's forget this one. So you can come to here, yeah. So you know you at 5 p.m. you will plug in your smartphone to charge, and you can predict how much energy you need, yeah. And you can calculate this delta factor, that is like energy remaining divided by energy demand, yeah. So if your phone is charged a lot, like 100%, you have a lot of energy until 5 p.m., right? But let's say if it's only 20%, right, then energy remaining is not that much, yeah. But it could be because you are going to do lots of things into your phone, your energy demand is too much, yeah. That means it's not easy to last the phone battery until 5 p.m. okay. So this delta factor, it says if it's less than 1, which means demand is much more than the remaining energy, right? You need much more than what is left. So what you can do here, then he kind of finds out the frequency at which you can reduce the phone to run, and this is kind of done again with some trials. So it finds the lower frequency so that the phone is not taking a lot of battery, yeah. So you can imagine what could happen. It's going to impact some performance, yeah. Might be your applications are slow or you are not getting the best user experience, but it's trying to ensure your phone battery will last until 5 p.m. okay. But for some other of you, it could be your energy remaining is a lot, yeah, and then demand is not that much. Maybe your battery is 100% charge, so you can run at some higher frequency. So your kind of quality of experience is not compromised, okay. And this keeps happening at regular interval. So that student set up like 1 minute, 2 minutes, 5 minutes, and keep doing this with the aim like You don't need, you can keep running your application until you go and plug in. Okay. So you can see this is kind of energy kind of management. So it can be applied other places as well, but that student has applied in smartphones. So something like we discussed, yeah, in data centers, sometimes there are renewable energy available, yeah, and that is not forever, yeah. So you can think like that renewable energy is maybe until 5 p.m. or something. So how you can maximize things within that limit, okay. So something like that can be thought through, okay. Again, some evaluation results. So I will tell like this one, like there is something called like default method that is in the smartphone. This is in all the smartphone at the moment. That is running. We took that method, and there is another method called like power save. So power save, like it says, right, you want to always run at the lowest frequency. Yeah. So in the phone, if you can open the operating system, you can change the default. So we did change. And another one is like quality aware approach, yeah. That means you always want the highest quality, which means you always want to run at the highest frequency, yeah. And this is another approach existing, proposed in the literature. It's called like user and battery aware resource management, okay. So in comparison to these, if we look our approach, basically we took the energy demand into account, yeah, like until the plug-in happens for charging, and we also take the user behavior, okay. So it's kind of a bit more learning with respect to the user, and we will see how the results are when we compare all of these. So this is the one set of result. So what we did actually, we took the phone and we started with different initial battery level, yeah. So we charge the battery full, we start with it. You are at 90%, you start with it. You are at 80%, you start the day with it. And 70% you start the day with it, yeah. So, and the phones, different people are going to use in different way, right. So we are measuring active time, yeah. So like until what time you can be active, yeah. Another thing we looked is final battery level, yeah. So you can see like if you are starting maybe at 90% initially, at the end of the day with different approaches, you will still be left with some battery, right. But if you are starting with like 60%, like I said, if you started morning with 60%, by 5 p.m. you will have no battery level left, okay. And how much time you can be active, you can see, yeah. So if you started with 60, you cannot be active after this, yeah. Maybe by 3 or 4 p.m. your battery is gone, okay. So when looking these approaches, you can see power save first, yeah. Power save is something is always going to run everything at the lowest power. So you expect this one will be the best in terms of lasting for the whole day, right. So you can see this one, power save, the star one, the active time for it is the longest, yeah, okay. And for this, the same will happen with the what is the final battery level left, okay. But if you go the quite opposite approach that cares only for the performance, yeah, that will always run at the highest frequency. So in that one you will see the active time will be the least, right. And again the final battery level will be quite low. And other approaches are somewhere in the middle, and same our approach is somewhere in the middle. You can see here quorum. So but when we look like we try to combine all the metrics, yeah, like we want to be active, we want to take minimum energy consumption, then our approach sits in the middle and performs better than existing approaches, okay. So these are some quality of experience results for different approaches, yeah. So you can see how much they are getting with different initial battery labels, and more details are in this paper, yeah, okay.
This approach is like kind of balanced.
Yeah. So the only main aim was, this student is from Nigeria. So in Nigeria, people worry more about battery level or everything, these things. Even in here, right? You leave your room, you always check your battery level, right? You always want to make sure by the time I come back and plug in, my battery should last. Yeah, but sometimes when you go out, you are going to check emails. Yeah, you are going to call someone. So you have a behavior, you also can't control it. So you can keep doing it, but you will not get the best performance. Yeah. So even if you are watching some video or something, maybe with this approach he has developed, like, it will reduce the brightness level automatically, just to make sure by the time you come back to the plug-in, you basically have the battery. Yeah. And it's also one of the most worrying factor for human. Yeah. We always worry, like, how much is our battery level. Even if sometimes it is 80%, we fear, like, okay, I do not know whether I will come back with some battery left or not. Yeah. Okay.
It is kind of dependable on the timetable now. When you will charge your phone, it will get the time ki is time to charge karte hain.
Yeah. That's true. Also, sometimes people are in, like, mountains, in travel, there's no facility. If you can have this kind of technology, it can ensure, like, just say I want my battery to last for 3 days. Then it will not allow you to run some applications that are very kind of power hungry, or the ones you are running, you will be penalized in performance little bit. Yeah. Okay. So that was for, like, a small scale system. So how that kind of intelligent computing can be done for servers. Yeah. So server is again like a big chip that has many cores, right? So what typically you do here, you can have lot of applications that can arrive at different times, right? And then you basically allocate those applications onto the server, basically on the cores, and you try to optimize something, right? So for the servers, one of the aim is throughput, like you want to run as many applications as possible within a certain time, and you also want to optimize energy consumption. Yeah. So that the energy bills can be lower. Okay. Similarly for data centers, I think we have seen this, so we can be quick. So you can have the data center environment, you can have different users across the globe, and they can submit their job, and you can try to optimize value and energy consumption. Like I said, value is the money, the profit for the data centers. Okay. So these are the two things basically I would say for sustainability, but we also saw there could be throughput optimization. Yeah, there could be some kind of security optimizations as well. So if it's about security, there could be kind of some secure zone, non-secure zone. Yeah, if it's kind of something from the defense sector or something, you put things in the secure domain, secure kind of nodes. Okay. Okay. So now we will look one of the approach that was developed in my group. We call it monitoring enabled adaptation in data centers. Okay. So first let's look, there is no adaptation. So adaptation means you start on one core, but then you switch on another core. So but this one is without adaptation, so non-adaptive. Yeah. So let's say you started with something like this, yeah, and you had 3 cores. So this is just an example. And when this task arrives or job arrives, these 2 are busy, yeah. So it will allocate on core 3, and even if they are free, it will keep executing it on the same core, yeah. So from this we learned, like, there is opportunity when this one becomes free, we can try to shift the workload here, yeah, or distribute. When this one free, we can distribute on 3. But in order to do that, you need some mechanisms, yeah, some monitoring or check on regular intervals, yeah. So this is what we exactly did. We defined some regular interval, or you can say checkpointing, yeah. So we check here, and this is like maybe 5 minutes interval or 2 minutes interval, and those regular intervals we check like which cores are free. Yeah. So for example, here you can see this one is free, so that job is cut into 2 and put on 2 cores. Again, at other checkpoint we saw, okay, the third one is also free, so you chop that into 3 parts and distribute. And with this way you can see this one was completed here, but this one is completed here much early. Yeah. Another thing we could do, you can see here we are executing the task always on like some different voltages, right? But here we can also think of doing the same, like similar kind of adjustment with the voltage as well. Okay. So in summary, you can see this one is completing very late, right? So remember I said there are organizations, if you complete their job fast, you get more money. So this will be basically low value. Yeah. Also it will have high energy consumption because it's running for a long time. Yeah. So you're paying power for a long time. The one at the bottom, it has early completion, so it will have high value. Yeah. And it also has low energy. Yeah. And these are some results. So here you can see on the x-axis, this is like number of nodes in a server or in a data center, 2 nodes, 3 nodes, 4 nodes, 5 nodes, 6 nodes. Yeah. This is like number of servers. Okay. And this is the value, that means money, and this one is the energy. Okay. So the bars are basically the value and the lines are the energy. So if you look all these approaches, you will find the one that is this adaptive approach, we name it as like value and energy adaptive optimization. Okay. So in that one the value is always highest. Yeah. But if you look the energy consumption for it, that's this one, it's not the best. Yeah. So the orange one is better. Yeah. So it's like we got more in one metric but we lost in another. Yeah. But again, like I said, it depends what is your aim. If you want to combine both of these together, like energy and value together, we found out like then our approach is better. Okay. It's getting better results. Yeah. So it's like this way you can basically hit both the metric. Yeah. Another way to do is, you know, even whatever is energy, right, you can convert that to money, right? Like this is like how much the data center companies are paying. So that one can be also in kind of value, and then there could be one plot only. Yeah. So there are many ways basically to consider it. Again, more details are into this paper. Okay. All right. How much time we have left? Like 20 minutes. Yeah. I don't know how much slides I have left. Okay, so I will try to be slow, but sometimes if I feel like it's easy, I will try to be fast. Yeah, so we can go at the end as well. Okay. So another work we did is like, again, regarding sustainability. Yeah, reliable distributed inference on edge devices. So let's look like, first of all, why we need distributed inference on edge devices. Yeah. So you know, DNN inference is increasingly being executed on edge device, right? Like I told you, there are going to be more and more edge device, and not all the data can be sent to cloud. Yeah. So even DNNs are going to run on edge device. Yeah. And there's other advantage as well, right? You get latency is lower. Yeah. Like if it is autonomous car, you can't run the AI model on the cloud. It has to be running on the car because it has to take the decision immediately. There are some other advantages as well. Yeah, privacy. So the data is not going out of the device. Yeah, so you are secure, more secure with the data, and always on availability. So wherever the data is collected, that kind of system is on. Yeah, for cloud, you don't know, maybe it's overloaded already with something. When your task arrives, it cannot do anything. Your task might be put in the queue. Okay. So that's one advantage, and DNNs are also computationally intensive, right? So if you take a very small device, maybe you cannot fit all of it, the whole model, yeah. That is why we try to distribute on edge device, yeah. For example, if there is a big DNN model, maybe it cannot fit on my phone, yeah. So what I can try, like I can try couple of phones, or my phone and laptop, or maybe my TV in the home. I can fit the whole model into these three devices. So I chop it and put some fraction here, some fraction there, and some fraction there. That is why this kind of distributed DNN is coming into picture, yeah, because that is still very big and cannot be executed on a single device. Okay. Okay. So now what we proposed is something called like fluid dynamic DNNs that can provide more reliable inference. Yeah, it's again related to sustainability. It's like more reliable operations. So before looking at fluid dynamic DNNs that we proposed, let's look something that already exists. Yeah, so something that already exists is one is a static DNN, right? You take the 100% model and train it, and it's ready to be used. Yeah, but people also proposed something called like dynamic DNN. So this whole model, what they do, they take that like 25% of the model, they train it, yeah, like this one. So you can see this one is ignored, yeah, the dotted ones. Then they kind of incrementally add another layer, and they train that as well. And then they incrementally add another layer, they train this one. So this is like 75% of the model. And then they add the last layer, train it. So that is like the dynamic DNN, how people have done, yeah. And static is always fixed, yeah, it has all the layers, okay. So even with dynamic, even if there is 50% of the model, it's not going you to give the results like 100%, but it will give some results, yeah. That is how dynamic DNNs came into picture. Also, if this model is too big to fit into one device, you can use only 50% of the model, yeah. You can compromise on the accuracy, but you can fit into the resources that you have available, okay. So what we proposed is called something like fluid dynamic DNNs. So here what we did, we tried to train the upper part, not starting from the left side, rather you can say something in the middle. So this is like upper 25% model we trained, yeah, and then we trained this one as well, okay. So this is like upper 50%, upper 25%. Maybe it's not clear yet what's the advantages, but it will be clear in a bit, okay. So now let's say that whole model has to be distributed on two devices, yeah, maybe two smartphones. And this is what we already covered. So if it is a static model, yeah, let's say half is going on the one phone, half is going on another phone. If this one fails, the whole system is not going to work, yeah, because you get the output from last couple of layers, yeah. If you look the dynamic, if the whole like static fails, you can still load this model A and B, right, and then you can still get the output. And fluid, you can always get that, yeah. So fluid is like combining this one with some training from the upper part as well. So in this case, dynamic and fluid are going to give you the similar results, yeah. So in fluid, it's like part is dynamic, and then C and D, the upper part is on the faulty node, okay. So you can get will get the similar results, okay. So here we are assuming the right device fails, yeah, and there is always like master worker kind of model. So here is like worker is failing, okay. Now if we say the left device fails, the master fails, okay. So you can see the left one is red, okay. So static is not going to give any results, yeah. And if you look the dynamic is also not going to give you any results, yeah, because dynamic is like the training done in an incremental way, okay. So you can see if AB fails, so there is nothing like CD in dynamic DNNs how it is trained. But if you look ours, we kind of have trained the upper part. Yeah, so this part is still going to work. So you will still get some results from this. Okay. So if you kind of do the training in a kind of some twisted way, even if one of the device fails, you can still try to get the outputs, and this is more reliable. Yeah, it makes the system reliable, so you don't need to throw the system out. Okay. And these are some results of throughput and accuracy for these three approaches. Yeah, and these are a couple of combinations, like only worker is working, or only master is working, or both master and worker are working. Okay. Here we have like for the fluid, 2 bars. One is for like high throughput, another is for high availability. So just kind of to test 2 different situations. Okay. And this paper was published last year in a conference. So again, for more details, you can look into that. Yeah. I mean, there are 2 things. One, we don't have time. Other thing is, if we go into too much details, we cannot cover other things. Yeah, and it can also be very confusing. Yeah. Okay, another thing for sustainability. So there is a trend, something called like multi-chiplet systems. Okay. So if you look like how the computing started, right? We had this transistor level. Yeah. You remember, first transistor was discovered. It did something. Then there like gate level things were made. Then ASICs were made. Yeah, just some for some specific purpose. At the moment, like we are at system on chip, whatever we discussed. Yeah, the chip in the phone, laptop, everything is system on chip. But in future, it is predicted there will be something called like multi-chiplet system, or 3-dimensional integration. Okay. I will come to it, what exactly is multi-chiplet system. But before that, I wanted to discuss, maybe discuss, not ask, why do you think is this trend? So we don't have time for like basically typing. So let me tell you why this thing is coming. So when we are kind of producing these monolithic ICs, right? You feel like there was kind of this nanometer, right? They started like long back, 90 nanometer, 60 nanometer. At the moment, there are 7 nanometer chips. People are trying now 2 nanometer. And there is no way like to go much lower. Yeah, you can't go into picometers. Yeah, because chips start failing, heating, more and more heating. So again, there will be no way to go forward. That is why you might have heard people say Moore law has ended. Yeah, you can't pack up more and more transistors. If you can't pack up, the trend is coming like multi-chiplet system. So you take different chips, like one processing element. It can be CPU, it can be GPU, but it is very kind of a small module, and try to integrate that into a kind of big chip, and those can communicate with some mechanisms. There are a lot of ways. One of them is called like interposer system. So some companies have started developing the CPUs, GPUs based on these chiplet models. So very soon, I think AMD is going to release one chiplet based chip. Yeah. Okay, this is coming for that reason. Again, you may think why multi-core system came into picture. Yeah, it was like the single processor Pentium. Yeah, Pentium, then P1, P2, P3, P4. Yeah, there was nothing after P4. They were like dual core processor. So again, you could not increase the frequency to very high level because it was getting very heated. So you thought, okay, let me run low frequency but use more number of cores. Now, even with that kind of trend, it's ending. So people are thinking it will be like multi-chiplet systems. Okay. I think few things we already have said. They overcome limitations of monolithic dies. Yeah. So if it's monolithic, it's like basically it's again like very low nanometer technologies, making that is very costly, and they cannot be scaled. Yeah. So there's end to the nanometer. and if you are doing that, yield is also very less. Yield means like how much many of the chips are good in comparison to whatever is produced. So the process is so complex now, the lot of chips are getting defected, yeah, so cannot be used. And with this multi-chiplet kind of things, it enables heterogeneous integration very easily. Heterogeneous integration is still there. So there are CPU, GPUs, memories all integrated. But this one on top, it allows you to integrate components from different nanometer technology node. So at the moment in the SoC, all CPU, GPU memory is on 1 nanometer technology, yeah? Either everything 35 or 28. But this one will allow, maybe CPU is at 65 nanometer technology, GPU can be at 30 nanometer technology. So those kind of integrations are possible, okay? And it also facilitates reuse of proven IP blocks. So it's not like you need to keep developing something new. So whatever is existing, if it's already very good, you can just integrate it into the multi-chiplet system, okay? So there are a couple of other benefits from sustainability point of view as well, right? You can have some specialized chiplets that can reduce energy per computation, yeah? You can design the system in a way. And these also kind of facilitate modular upgrades, yeah? It's like one of the chiplet fails, one of the processing element fails, you can always upgrade that, yeah? This way you can extend the lifetime of the system. Whereas in my phone right now, if my GPU stops working, everything is gone, yeah? Or if my memory stops working, everything is gone. But this one can facilitate easy replacing, okay? And like I said, faulty chiplets can be replaced easily. And smaller dies improve yield and reduce waste. So with this one, like the die size will not be that big, yeah? So it's like there is not a lot of waste, you can say. I think this one maybe we can skip. So one of the students actually did some work. He took some applications. He took a kind of chip that has 2 chiplets, and he looked like how the existing approach will map the tasks onto it, and then he developed some communication minimization approach. So again, balancing the computation and communication from the multi-chiplet system point of view, okay? I think more details are in this paper, so that was just published last year, okay? Okay, so again, due to time, we are not covering everything, but I also have some work on reliability and aging management. So how to increase the lifetime of electronics. And those things are already talking about it, but there are some more works from the resource management point of view. So when you get time, you can look into those papers, okay? Okay, so now let's look like what can be the emerging trends from now on, yeah? So these are my thoughts. You should not take like this is what the world is thinking, yeah? The world may think in different way, or different people may think in different way. So one of the things I think is there could be increasing type of covert and side channel attacks. So we have seen some, right? The timing, temperature, sound, but there could be other ways coming into picture, yeah? People can think of different kind of physical properties. So basically when we have more and more types of these attacks, all of this needs to be considered, yeah? So as like I said, as an attacker, think what is other extra property that you can use to attack the system. And another thing that we should do, we should have some joint consideration of various attacks. So you can see like some people just consider like maybe temperature side channel attack, and some consider only acoustic or sound, and some are caring only about the password, some are caring about only the malware, some are caring only for the phishing. So nobody is considering everything together. So we should think in a way how we can come up with a solution that considers most of it, or the most promising ones, yeah? And but you have to also think the solution should not be very heavy, yeah? It should not take a lot of power and energy, okay? and this one is actually published in this paper, this figure. Okay. So try to consider as many of them as possible. Again, like if you look again the whole literature, some people consider sustainability secure, some people consider security separate. Yeah. So there is a need basically to jointly consider these. Okay. In some of the works I demonstrated, I showed you, yeah, like the kind of bit error rate and the power. So it was kind of a joint consideration, but more and more needs to be done. Okay. I think for sustainability, we already have said it's mainly about increasing the lifetime and reducing the energy footprints. Okay. So if we are considering both, basically we need to find the right balance, yeah, between the security and sustainability. And one thing I have missed here, we have not covered, like I told you, yeah, there is a lot of sustainability problems before the time we get the product. Yeah. So a lot has to be done there as well. Yeah. So during the design or manufacturing, lots of sustainability aspect has to be done. Some research is being done in that direction, but not much. Yeah. And again, everything is going to be like in the form of AI applications. Yeah. So think always from these AI applications and AI workload. Okay. And cost is the most important factor. Yeah. So you cannot come up with any kind of solution, maybe that is considering both sustainability and security, but if it is very costly, then nobody is going to use it, nobody is going to pay for it. Yeah. So always think in cost effective manner. Okay, another trend that I feel can be is hierarchical management of multi-cluster platforms. Yeah. So with increasing complexity, yeah, and technological advancements, so we can see like there are multi-cluster platforms. Yeah. Like in the phone, I saw you, there's a big cluster, there's little cluster, and there's GPU cluster. Yeah, 3 clusters are already there. So similarly, MediaTek, you may know, their processors also have 3 clusters. So multi-cluster architectures are coming into picture. Similarly for chiplets, I saw you, right, the chiplet 1, chiplet 2. One chiplet can be one processing element, or one chiplet can itself be a multi-core chip. Yeah. So then there are like each of the chiplets are a cluster. So these kind of things are going to come into picture, and they will require some kind of hierarchical management. Yeah. So where one of them can act as a local manager that can basically decide how the things are going to be managed. Okay. And then so one of them is like global manager, but then at each of the clusters there is a local manager. Yeah, it's managing locally, and then something is managed globally. Again, it's kind of the concept is like an organization. Yeah, like for IIT Guwahati, there's a director. Yeah, he's a global manager, but then there are a lot of departments, and the head of the departments are local manager. So they are managing. Yeah, but this global manager is not talking too much to the students of that department or the faculty of that department. He is talking mainly to the head of the department. So the head of department is local manager, and the director is the global manager. So similar kind of hierarchical management is needed into these kind of systems as well. Also, to kind of reduce the management complexity, a cluster can be divided into another subclusters, right? For example, like I said, head of the department, right? Sometimes if the department is big, there could be deputy head of the department, or head of education, head of research. So they can deal with different kind of things. Yeah. So again, if the platform is big, you can have subclusters. Again, these kind of things are already happening. Samsung Galaxy S10 mobile phone started this. So they had a cluster, and that cluster was divided into 2 subclusters. Okay, so that's going to help in the management. And finding the best hierarchical management policy is challenging. Yeah, if like so many things are there. Okay, I don't think we have time for this question. I was like, can you think of any other emerging trends? Yeah, so I talked few. Like you could be more and more side channel attacks. You need to consider security sustainability together, and hierarchical management is important. Yeah. Any other trends? I think don't worry because we do not have time. Yeah. But you can think about it. Yeah. What can be there? So with this, I would like to acknowledge my many members of the group. I think not everybody is listed because this research, if you remember, I saw something from 2010 or something. Yeah, so it's like 15 years. So there are many people involved. And thank you. Any questions? No?
In the BSF,
Yeah.
you can use within that genetic algorithm, right? So instead of that, can we use any optimizer tool to sort that?
Yeah.
So how we decide that, right? Which one to use?
I think if you want to use any optimizer tool, the main task is how you fit your problem into that optimization. Yeah, it's like how you design the input to that. Even for the genetic algorithm, I said, right, you have to design the genes in a way it represents your problem. Yeah, so one of the gene is representing how the task is mapped on the core. A few genes are representing what will be the voltage frequency labels of the cores. So you can use other optimizer tools. Yeah, there are, like I said, turbo search, integer linear programming, all these are used. It's just they work nice, but they're for different purpose. Yeah, you need to feed your problem in a way they understand it. Yeah.
So we cannot count that this one will work better in this case. Can we count that?
I think you need to evaluate. Yeah, so I think maybe you are saying which one is better, like genetic algorithm, turbo search, or maybe reinforcement learning, which one is better. So I think first of all, like you should think like yourself, which one, what is your situation, and which one will be better. Yeah, and then you will be left with some options. Yeah, and then you kind of try all of these and find the best from there. Yeah.
Thanks so much.
Okay. Any more questions? Okay, if not, then it's lunchtime. Yeah, and this is my last lecture. I think from here Dr. Moumita will take, and tomorrow Dr. John will have lecture. Yeah, on Friday I think you have some test. Yeah. Okay, good. That's done. Anything to be done?
No, it's okay. I just want to thank you.
Okay, no problem.
Okay, so we should thank Dr. Amit for coming all the way here. Okay. And yeah, so this is his last lecture. Hope that you come again
Of
and
course,
give
yeah.
other lectures also here.
On the
And,
topic. Yeah.
The topic was very good, and I am sure everybody has gained a lot of knowledge in terms of security and system. Couldn't start on time. Apologies for that. So today we are going to work on a Wireshark tutorial. So as mentioned yesterday, I had asked you all to bring your laptops and if possible, please start downloading Wireshark. Okay, if you have already done that, good. Okay, so today we have our research scholar Elena Sinha with us, and she will be giving you a brief overview on Wireshark and how to use it for different questions that we have already prepared. Okay, so before we start the class, so I just want to make a few announcements. So tomorrow there is the schedule is like 11 to 1 there is a class by Dr. John Jose, and day after tomorrow we have an exam. Okay, once you give the exam, then the certificates will be given. Okay, so I'm sure that you have already been told some of the data that we require from you, that is your some details and passport size picture probably. So that will be conveyed to you later on by our volunteers. Okay, all right, so yeah, over to Elena.
Thank you, ma'am. Thank you everyone for your patience and time. So before we delve into Wireshark, let's speak about the water shark. So we all know the animal, the shark, which stays underwater in the ocean. So what does the shark usually do? Like we have seen movies, Jaws. Anyone? Yeah, it hunts for its prey. And the way it does is that it tries to sniff blood, and it goes towards its prey. So Wireshark what happened? No, it's a display issue. Yeah. Don't cross it.
Top right corner, middle button.
The buttons are all disabled for now, but we can function this way. Thank you, Krishna.
It is not moving. Can you shift them this way?
What is the issue? Idea as well.
Everything is getting disabled and she's unable to scroll. The buttons are also not.
Wait, why are you connecting via USB-C? We don't get HDMI. Give the dongle back to me. Dongle? It's not, sir. It's alright.
Dongle will take
PPT.
ब्राउजर में प्रॉब्लम है PDF में चलेगा जस्ट डाउनलोड PDF
It's okay, so we can just do it online.
what you can do is
I'll just check if it is opening on the browser. If not, the PDF is downloaded.
I think it is good. Yeah. Now we can do it.
No, ma'am. No, not
You don't
me.
need it?
No, ma'am.
Okay.
Thank you, everyone. Sorry for the technical glitches, and thank you for everyone for coming together. So, just like the water shark does the same thing. So, it sniffs packets on the wire, on the network, and then it tries to capture them and analyze them. Almost parallel to a CCTV camera. So, a CCTV camera records everything that happens. Let's say we go in an airport, so it will capture every person that comes in and out. And whenever required, we can obtain all the details and study every person's movement inside the airport. So that's the analogy. So we say that in networking, the connections may be temporary, but packet capture is permanent. So Wireshark was born on 2nd May 1998. Previously, there were many networking tools, but they were closed and very expensive, and not many people could access them. In 1998, Gerald Combs, he made Ethereal, which was open source, and it suddenly, he tried to solve a personal problem, but that it suddenly became very popular. People tried adding patches to it, and then a lot of global contributions happened, and today whatever we see is the Wireshark. So it's so popular that every month we have around 40,000 downloads. Let's see how Wireshark sees the packets. So if we see the protocol stack, we have the application layer, the transport layer, the network layer, and the link layer. Wireshark taps into the packets at the link layer level. So we have an application layer message which at the transport layer we add a header, and then we see a transport layer segment, which then gets passed on to the network layer, and from the network layer, the link layer collects the network layer datagrams, and then that is what the Wireshark taps into. So let's see how Wireshark captures and analyzes the packet, the structure. So we see that there is a device and the packets travel to and from the device. On the extreme left we have the protocol stack. So the application layer is at the user space, and then we have all the other layers. We see that Wireshark copies all the link layer frames and keeps them in a file called the packet capture file, also known as the PCAP file. Apart from that, we also have a packet analyzer, which is very important to us because that is where exactly we see all the details of the frames and all the TCP segments, all the network layer datagrams and details. We'll shortly look at that. So let's get started, and before we fire up Wireshark and see how it is, let's try to get introduced to some of the interfaces that we'll be seeing there. Meanwhile, we can maybe download it in our systems and look through. If you want, then these are the installation steps on Ubuntu and Windows, but I guess we can carry forward. So when we open Wireshark, when we fire Wireshark, we usually have two panels. The topmost panel has the PCAP files that were saved previously. Since this particular Wireshark version is downloaded very recently, we do not have that panel. Beneath it, we have all the link layer interfaces like Wi-Fi or Ethernet. The squiggly lines that we see are those packets that are captured. Maybe we can select Wi-Fi. Once we open, we have the menu buttons. The two most important buttons are on the top right. The blue shark-like fin, which when we start, it captures the packets, and then the stop button, these two buttons are the ones that we will be using mostly. We also have all the list of packets that are captured. We can maybe stop it, select a packet, and all the details of that particular selected packet is what we see in this screen. And the details of those packets in ASCII or hex can be seen in the right hand panel. So as the first exercise, let's try to see the network statistics, and we'll try to see the throughput, round trip time, the average packet size, number of packets lost, and the number of TCP and UDP packets that were captured. For that, let's try to open a browser first, and hopefully we'll capture some HTTP messages. Say we open iitg.ac.in. So we can check the network statistics. Once we see the net stats, we see all the TCP packets, the number of packets that were received, the header arrays, the datagrams that were forwarded. We can go to TCP. the number of segments that were received, sent and retransmitted because they failed on the way, and the current connections that are there. Similarly, to see the statistics on Wireshark, we can go to statistics, maybe input-output graphs. This is in packets per second. So, to calculate the throughput, we can change the y-axis headers to bytes. Or we can even go to TCP stream graphs and check for the throughput. I can't see anything. No. No idea why this is not firing up, but
When you open the Wireshark, suppose you open this one. Round trip time, because the access is very big, that's why it's not visible.
Okay.
It may be somewhere.
Okay, maybe this is the configuration of the axis, but usually we can see the round trip time graphs and the throughput graphs here. Since Wireshark is installed very recently, I'm not able to fix this right now, but so for the number of packets lost, we can see that, or if we want to check the number of TCP and UDP packets, we can just go to we can go to the stats, protocol hierarchy, and maybe we'll see the number of packets for TCP and UDP. Here, I guess 98% of them are of TCP packets, but I mean no UDP packet is captured yet. Similarly, for if we want to calculate from that stats, we can get the input from the input bound throughput and the output bound throughput, and maybe we can calculate. Similarly, for the average packet size, we can see the particular values of these fields, and maybe we can calculate from there. Let's go to the second assignment, which is understanding TLS with Wireshark. So in transport layer segment, TLS, the client and server communicate, and they try to handshake and settle with a particular key or a particular encryption system. So to capture. Let's try to see a TLS handshake. TLS. We can go to the filter section and TLS.handshake. Dot type. Since we want to see the symmetric key algorithm that was used to encrypt the HTTP data, this will be done during the server hello. So we'll try to see the server hello messages. So type equal to 2, and we can see a server hello message. We can click on the triangle button on transport layer system. We have selected one message, and maybe we can select from the record layer handshake protocol the server hello. Is anyone doing along with me? Okay. All right. So we see the cipher suite, which is TLS AES 256 GCM. So AES 256 GCM is the one.
Okay, please.
Yes. So in TLS we have this client hello and server hello. So in client hello, a lot of handshake protocols will be sent by the client. The server hello, one will be selected by the server and it will be fixed. So once we put the filter as type 2, we will select, we'll have only the server hello messages. Now once we select this message, we can see the frames, the Ethernet, the IP protocol, TCP protocol and the TLS. So we can expand transport layer security. Is it done? Okay.
So everybody is done with this? Are you doing it together? Please do it. Yeah? Please do it.
Analyzing the software.
Yeah, but we want you to also check that whether you are getting this answer or not. Okay, whether you are getting the same thing that is being shown in the screen, then only we will learn about it, right? So please.
Yes.
For you, yes. Yes, yes. So maybe I can go and check. Okay.
We can see that the transport layer version is 1.2. The random is the random number that will be used. Is anyone having a cipher suite that is different from this? Different handshake protocol? 0x?
0xC030.
No, the cipher suite. It will be something similar to this. Maybe cha-cha something. Okay, this is the one with AES 256 GCM. Someone else? Same? Okay. So let's see the other question in the slide.
Can we wait for a little bit more?
Yes, ma'am.
Let's see.
Can I go and check?
I can check. Please go. Are you getting? You are starting.
Okay, so the next question is, in which TLS message is the algorithm negotiated? So the negotiation happens in the server hello itself, which was discussed right now. What is the packet number of the first encrypted client or the server application data? First encrypted client to server application data. So we can put the filter number as 23. Okay, yes, 23. So we'll go for the record content this time, not handshake. So record content dot type equal to 23. And the first application data message will have a particular number, which is the packet number. Is everyone getting this number? Anyone higher than 146 or maybe much lower than that? Yep. Okay. So the next is what is likely inside the first encrypted application packet. So once the first encrypted packet will have some message, maybe an HTTPS GET message. The next is which packet shows the client sending a TLS shutdown message. For these we can see some alert messages. So we can go for the content record content type as 21 because they usually show the application alert messages. Is anyone getting this filled up? Okay. 1 second. Can we, I don't have those packets. Okay, but it's an encrypted message. since Wireshark cannot capture encrypted messages, but the alert message is probably a shutdown, TCP shutdown message, TLS shutdown message. Anyone else who got it? No? No? So these are some filters that we can give. Just to show the client hello, we can see the select the type as 1, for the handshake type server 2, and if we want to see the change cipher specifications 20, 23, 21, and if you want to restrict it to only one single TCP stream, we can specify the number. So let's see. We can then go for the next assignment, which is exploring ICMP with Wireshark. ICMP is usually used for diagnostics of some, if there is some failure in a router, or so through ping and trace routes. So
So anybody here does not know what is ICMP? No? Okay, have you heard of ICMP? Can you check now what does ICMP do? Okay, so it's a control message protocol. Alright, so what you generally find out is that from one node to another node. Okay, in general we check for trace route, etc. right, when we use ICMP messages. That means number of nodes that are there in between your endpoint and the other endpoint that you are looking at. Okay, so please check. Sorry, what you are saying?
He's getting ICMP V6.
No ICMP at all. You are googling ICMP and you are not getting ICMP.
He's checking Wireshark.
No, I'm asking you Google ICMP and then you find out. Okay. So now what we are going to do with this Wireshark is that we are going to check that use ICMP. How does it just see that how the packets are getting traced here. Just take a look at it. So these are the few questions that we will try to answer. Okay, please read the questions here. Okay, so has anybody done a ping in their laptop's terminal? You have done. So what do you see when you do a ping?
So our laptop sends a packet and then they receive the packet.
Hmm.
Then they show the latency and the jitter and all.
Okay. All right. And what about you? You wanted to say something?
No, I was wondering if jitter is shown, but I mean you have statistics that are shown at the end.
Okay. Okay. All right. So Elena will now show you that what exactly is shown. Okay.
can we maybe do an ICMP ping and then maybe check the ICMP messages?
Check. Are you guys getting there? You guys are getting? Yeah?
Okay. So maybe can we go to Wireshark and type in our filter icmp.type equal to 8. So the question is compare packets from traceroute versus ping. So that will give the traceroutes from ICMP packets from traceroute. Is it populated in Wireshark?
No packets.
Can we check? Okay. Okay. And then maybe ICMP.type equal to 11. Could you ping?
Yeah, so they are doing. What is the issue?
We need to ping first. No. Yes.
So first you are ping. Okay? But to ping the particular website. So if you wait, Elena, see when you pinged it
Yes.
last time, yeah. So when you are pinging, please see that how the responses are coming from that side. Okay?
Yes.
Then you can check for the ICMP.type it. Why you are doing this ICMP.type it?
Just to see the traceroute packets.
Yes. So for traceroute, type equals to 8.
8. Okay. No. Okay, this is for traceroute. The other question was no. Did it get populated for anyone? Type equal to 11. 11. Sorry.
What does like code 11 mean
Sorry.
for type 11?
I didn't understand.
I'm saying like how will we get 11 packets? Type 11 packets. Like we ping now.
Yes.
So we got 8. Type.
Oh. Yeah, we ping, but I don't know, the messages are not populated.
Can we try the next question?
Is there a hop with an unusually high delay in your trace?
Let's go to the trace route.
So we can go to the statistics and see the RTT.
I think you have to do a trace route again and then write it up. Is anybody else getting the ideas? Let's check. No statistics. So. Can you put just TCP there? Remove TCP. Just TCP. Now you do statistics.
Yeah, so every spike or down point shows the RTT of the particular packet at the time.
Are you people getting it? Not yet? Not yet? What about you two? Did you get it? Did you get it? Alright, we can go to the next one.
So we can see what is the IP address of our host and target address. So maybe we can select a packet. Expand the header. We can find the source IP and destination IP here. Can anyone check? Oh, it's there in the packet itself here. But yes. how ICMP error messages are different from echo packets. So this is a theoretical question itself. And what extra fields appear in an error message? Why might attackers abuse, and how can network security tools like firewall or IDS limit ICMP misuse?
So these questions maybe we can take up for ourselves, okay? Because these are theory questions, you can just go back, check Wireshark again later on, and then find out the answers to it.
Okay.
Okay?
Yes. So
Don't have time.
yes, these are some key filters, and these are some points to remember: that it doesn't capture unencrypted packages. We should make sure that we don't have any VPN. We can either turn off our browser or OS privacy for that. And that's all. Thank you.
So can we do a quick on this?
Recap.
Quick, QUIC, quick.
Quick is
Go back. Yeah, so HTTP and quick, right, are becoming defaults. So then
Okay.
let's see if quick can be done. Let's see. Let's check if we can do quick here. Okay.
to open the browser. Say YouTube.
Okay, let's not show it that we are trying to find from YouTube, right?
Okay.
Let's see. So we have got some things. Quick. When you use quick, you have got some things, right? Can you do the same thing like you found out a little bit of all the questions that we have done with respect to TCP. Now let's check if we can do something with respect to quick. Okay. So what are the statistics that you can find with respect to quick? Can you tell me?
Statistics are in source destination close.
Yeah. What else you are getting apart from source and destination?
Code, length,
So
Check.
anything related to security you are
Checksum.
getting? Anything related to security that we have studied yesterday? So what is the most important thing that you get it here? If you see, so it is using UDP, right? So it is using UDP, right? Okay, so quick is used over UDP. So yesterday what did we see? We have studied that TLS is the one that is used over HTTP with that. So we are basically using TCP, and on that the enhanced security protocol that we are using it is TLS, okay? And quick is what? It is a security protocol used with UDP, okay? So when you check that, so you will get that UDP is there. Then we have our basic statistics that is given here, the source destination side, and let's see if we can find something else here. Check the statistics. It's not coming, no? No, UDP, sorry. It's not giving me okay, let's see.
We can go to conversations.
Conversation, we are not doing a conversation, no? Okay, let's see. What do you want to say? What do you want to find out?
I think you can say something related to UDP, but nothing.
Hello?
It's okay, I think we can just. Another is with. It's okay. We are done with the class. Thank you. Okay, so essentially we are done with the class. Okay. Only thing is, if you have any questions and if you want to still go on with some of the questions that are there, you can just go ahead. Okay, we are here for some more time. Okay, thank you.
Thank you.
So what else are you getting with quick? Are you getting anything else related to just different from what we get from TCP? Or everybody shows TCP only, so that is why I asked. same thing in BCP or it's yeah. Okay, so
Repeating something for connection number. Repeat connection.
okay, so this is a homework for everybody. Okay, just go back, check with TCP, check with Quick. Okay, and then see that if there is different times. Okay, see that if you find something unique in that or not. Okay, this is a homework for everybody. All right, yeah. Okay, so thank you for today. All right, so next session will be Dr. John Joseph, and this is my last session. Okay, all right. So thank you everybody. Yeah. Okay.